All right. Well, good evening, everyone. My name is Brian Schutmer. I'm one of the forecasters here at the National Weather Service in Louisville. And I've got about 5 minutes till 7 right now. So we're going to give it another 5 minutes or so and let everybody start trickling in. Looks like we got, 92, 93 folks in right now. Last I checked, we had like almost 350 people registered. So should be a pretty good crowd, pretty good turnout. So yeah, just hang tight here for a few minutes and we'll be trying to begin probably almost right at the top of the hour, maybe a minute or so after. If someone wouldn't mind just typing in the chat window or in the questions window, if you can hear me all right and see my screen all right. Okay. Yeah, it looks like everyone's saying yes, so that's good. All right, so just hang tight for a few minutes and we'll begin 7:01 Eastern. All right, good evening, everybody. Once again, again, I'm Brian Schutmer with the National Weather Service here in Louisville, and I'm showing about 1 minute till 7. So we're going to give it about 2 more minutes here to let folks continue to trickle in, and then we're going to try to get started pretty much right at the top of the hour here. Got a lot of material to cover in this 2 hours here, so I want to get started pretty quickly. So yeah, another minute or two, and we'll get going. Okay, gonna go ahead and get started here. And I'm sure folks will still kind of trickle in here for a little while. We got several housekeeping items to get to before we kind of get into the meat of the presentation anyway. So again, my name is Brian Schuttmer. I'm a lead forecaster here at the National Weather Service in Louisville. And yeah, really excited to give this presentation, Advanced Storm Spotter. I want to say the last time that Louisville has done an advanced storm spotter was maybe about 10 years ago. So I think this is kind of long overdue. And we received quite a bit of feedback from you all last year, kind of requesting it. So thought it was a good time to go ahead and do that. And yeah, judging by the amount of people that registered, and got almost 200 people in here right now. So pretty good turnout. And can't ignore the fact that this is pretty good timing as well, considering what we might be facing tomorrow evening. So yeah, pretty good timing. So yeah, I did want to mention, wanted to say a little thanks to National Weather Service Wilmington, Ohio, and Charleston, West Virginia. I've adapted some of the materials from information that they had in their advanced spotter talks, and provided a lot of new information for the Louisville warning area as well. So, but in reality, this is really more like a regional type of a talk. Anything you see here is something that you can see, in our region or in our area specifically. So, some pretty good material. I'm kind of excited to share this with you all. So before we get started, I wanted to mention a couple things. Since we got a lot of material to cover, we're going to probably have to keep all the questions till the end. I'm just going to kind of try to keep going. I'm going to schedule maybe a 5 to 10 minute break, about an hour into it, about the halfway point or so. Also, I wanted to mention that there are, if you look in your little interface here with the GoToMeeting, there should be a handouts section. And there's several handouts that can supplement this. A lot of these are the handouts that we give out or bring to the basic spotter training, but they're good reference guides. A lot of tips and tricks and things to remember. It's a good guide to have around. So you should be able to click on those and download those as you need them. One final thing I'll mention, you'll have access to a certificate for this advanced spotter training. What's going to happen is the program is going to send an email. I think it says tomorrow. It says one day after, so I'm guessing it'll be tomorrow evening when you get the email. And basically, then that'll provide a link that you can go to fill out a form, and then it will email you that spotter certificate, and it will say advanced spotter on it. So that'll be good to have, but you'll just have to wait till tomorrow evening to get that email. So. And I'm going to keep my camera up here for a little while I'm doing kind of the intros and everything. But once we get into the meat of the presentation, I'm probably going to turn that off just so we have more space to actually view the presentation. So again, yeah, my name is Brian Schuttmer, lead forecaster, National Weather Service, Louisville, Kentucky. Before we get into it, I just want to tell you a little bit more about myself. We're going to be spending a couple hours here together, so I figured it'd be a good idea just to kind of give you a little bit of my background. I went to Ball State University up in central Indiana. I'm originally from southeastern Indiana, so really not too far, from this region anyway, where I grew up. And I've been in the Weather Service now for 16 years. 3 of those years were spent at the Jackson, Kentucky office over in eastern Kentucky. And then for the last 13 years, I've been at the Louisville National Weather Service office. So pretty much been in the Ohio River Valley my whole life, outside of an internship that I had up in Alaska back when I was in college. Some other highlights from college: did get to take a storm chasing trip out in the Great Plains for a whole month, and actually got 6 college credits to do it. I think we traveled like 14,000 miles through 14 different states across the Great Plains, and saw 9 tornadoes along with tons of storm structure. I included a couple pictures from that 2005 trip here. One was a kind of a ropey tornado up in south central South Dakota, Wongwe, South Dakota. A really nice shelf cloud down there in the lower left. Really impressive storm structure there. Then just a really nice picture of an updraft tower that you can see in the lower right-hand corner down in the Texas Panhandle. After I graduated and got in the Weather Service, I took another trip out to the plains, more as like a personal trip with some college friends, and saw a couple of really nice tornadoes. You can see there in 2009 out in the Oklahoma Panhandle. That top middle picture is a really nice picture of a wall cloud, an updraft base, and a precipitation core. So some good experience that I've had back in my past, and then working 16 years in the Weather Service, definitely on the operational meteorological side of things, gotten a lot of experience in that area as well. So happy to share that experience with you all, and pretty sure I got some good stuff in here that you all can learn and take notes from. And we've got a unique opportunity here, so I decided to take it since we have a pretty impressive weather system that's going to impact the area tomorrow. I wanted to take a chance to apply some of what we learned with respect to instability and wind shear throughout this presentation, and then actually look at real model data for tomorrow, and then apply that to the Storm Prediction Center outlooks. And so I think that'll be a kind of a neat opportunity to tie everything together at the end. So definitely want to hang around to the end for that. So before we actually get into the presentation, I did want to just go ahead and kind of brief you on tomorrow's expected weather. So these are basically our briefing slides that we send out to our partners. And just earlier today, we actually briefed the governor with these briefing slides that I'm going to show you. So anytime you ever want to find those, if you go to our webpage at www.weather.gov and then /LNK, or you can just click on Central Kentucky. And then that'll take you to our homepage. In the upper right-hand corner, if there's an impactful weather event coming, a lot of times we'll have briefing slides up here where I have the arrow pointing. So you can just click on that link and you'll be able to see those. So yeah, this is kind of our briefing that we've got going currently. When I made the presentation, it was early afternoon, so the timestamp's a little dated, but the information should still be good. So yeah, tomorrow night we're looking at a pretty strong storm system. Surface low is going to track from the upper Midwest into the Great Lakes region, and there'll be a strong cold front that trails that. And we'll get pretty warm and unstable out ahead of that cold front, and so we're expecting a pretty strong line of storms, especially out over the mid-Mississippi River Valley. And then we do expect some weakening as it gets further east, and Western Kentucky has the greatest threat. But then as you get further east into Central Kentucky, Southern Indiana, and then over into East Kentucky, that threat should gradually diminish. And by the end of this presentation, you're going to know why that is going to diminish. We're going to go into pretty great detail about the ingredients that storms need to survive. So looking forward to showing you all that. But yeah, definitely a threat of strong and damaging winds. That'll be the main threat. But this is the type of environment that we can get spin up tornadoes as well. Especially further out west, as you get towards the Missouri Boot Heel and Western Kentucky, Southern Illinois, and then down into the kind of the Ozarks region of the mid-Mississippi River Valley there. So just kind of give you all some timing of when to expect things. If you live out in Western Kentucky, it's going to be more of an evening event, 6 to 10 p.m. in that time frame. I didn't include Southern Indiana on this, but basically you guys can kind of consider yourselves in that second tier, that 9 p.m. to 1 a.m. time frame for most of the Southern Indiana counties that we cover. And then as you get out east of I-65 towards the Lexington area, it's going to be more like a midnight to 4 a.m. time frame. And then the system will blast through pretty quickly and should be pretty much out of Eastern Kentucky before sunrise. So that's the expected timing, and that timing has been pretty stable, pretty consistent. So if it's going to fluctuate, probably not all that much that it's going to fluctuate, maybe an hour or two here or there, but those should be pretty solid time frames. And then once the storm's passed, again, they'll have the threat of some damaging winds and perhaps a few spin up tornadoes here and there. But then it's going to be windy outside of storms, just given how strong that low pressure is. And so really through the rest of Friday night into Saturday, especially Saturday morning, we're looking at sustained 40 to 50 mile an hour winds. And you may have some gusts, 55 mile an hour plus, which, it's not going to quite be like the March 3rd event, but, still, widespread 40 to 50 mile an hour winds can easily knock down some trees, power lines and things like that. If there are any trees left standing, as windy as it's been this spring and late winter. So, but anyway, that's kind of what we're expecting, pretty high confidence in those winds. You're going to see them regardless of if you see them with the storms themselves, but just outside of any storms, it's going to be pretty gusty again, later tomorrow and especially into Saturday morning and through the day. So that's what we're looking at. Again, we're going to revisit tomorrow's weather event at the end of this presentation, and we're going to look at actually some model data and apply that to what we learned. So like I said, you're definitely going to want to see that. I think that's going to be a good way to tie everything together. So, okay, so let's talk about what's going to be covered. And I'm going to go ahead and turn my camera off just so we can make sure we see the whole presentation. And let's see here. Okay, it should be off. All right, so it's not a prerequisite to take, the basic spotter training before you take this. Obviously, we think that's ideal and that'd be the best way to do things. But you're still going to be able to pick up on plenty of things throughout this presentation, and we're going to cover and kind of review some of the stuff that was in the basic spotter training anyway. So for those of you that have taken basic spotter training, you get a lot of good information, and you can almost kind of consider that to be storm spotting 101. Well, we're gonna kind of take it up a step, take it up a notch. You can almost consider this being storm spotting 201. And there's several different things you can do with an advanced spotter course. You could focus it more on tools and resources that help you, gather information, whether it be smartphones, tablets, things like that, radar apps, things like that. We're not going to do that so much. I really want to focus on storm structure, actual visuals, what you see with respect to storms, and why that's happening. We're going to get into pretty good detail about why storms do what they do in certain environments, and almost even how to look at that yourself to kind of anticipate what type of storm mode you have. Then we're going to apply that also to radar signatures, because everybody pretty much has radar on their phones now. And so yeah, you yourself can actually look at storms and know what you're looking at and what type of storm mode to expect. And that's helpful because then you know what type of hazards to expect with those storms. So I think that'll be good. And then we're also going to give you some useful tools. Again, a lot of people who take an advanced spotter type of a class are more interested than your normal person in weather, or are looking to become more interested. So I wanted to give you some tools that you can really immerse yourself in it if you'd like. So yeah, I think we got a lot of good stuff. I'm going to go through it. Again, about 10 to 15 minutes here is going to be kind of your basic review. And so if you've taken a regular storm spotter class, a lot of this is going to look familiar to you. But again, we'd like to build that foundation so we can go kind of the next level up and really get into some of the advanced stuff. And then, yeah, a lot of the time on how and why storms form, signs of storm strength, which I think is important. Since a lot of people have radar apps on their phones now, we're going to look at hailstorms and signatures on radar. And then again, that the first part of how and why storms form has a lot to do with instability. I saw someone ask, what is CAPE? CAPE is another word for instability. It's actually an acronym. It's convective available potential energy. In simplest terms, that means fuel. It's fuel for thunderstorms. So in the how and why storms form, we're going to talk a lot about that. But then when we get into the storm modes, so that is what type of storm you're looking at, that's more dealing with wind shear. Wind shear drives what type of storm you're going to see. So a lot of detail about that as well. So all right, let's go ahead and dive in. And again, this is basic review, but we're talking mainly about thunderstorms, damaging wind, hail, tornadoes, that sort of thing with this advanced spotter talk. But I don't want folks to forget that flooding is Kentucky's #1 weather killer on average. So any given year, on average, flooding is going to be your biggest threat. And it's the same for Indiana. I got you all in the next slide. Now, any one year you can have a particularly bad tornado outbreak or something to that effect. But on average, flooding is your most deadly hazard. So, and most of that comes from flash flooding, folks driving into flooded roadways. They think they can make it, and that water's a lot deeper than they realize, and they get swept away and trapped. And so really a lot of those deaths are preventable. So we really want to just remind everybody, turn around, don't drown if you do see a flooded roadway. Just a couple of highlight years on this graphic, 1997, those were the big Ohio River floods. And it wasn't just the Ohio River, it was, surrounding river basins as well. But that was certainly a year with a lot of flood deaths. And then like we talked about, though, you can get a year where you have a particularly bad tornado outbreak. And, for that year alone, tornado is maybe the deadlier hazard. So 2012, I think a lot of people probably remember that day pretty well. For Indiana, it was the Henryville EF4. The track just 20, 30 miles north of Louisville there. And then, West Liberty over into eastern Kentucky, both strong to violent tornadoes. So certainly a memorable day there. And we lose folks to lightning every now and then. Everybody wants to be out mowing their grass, and doing it right up to the last second till that storm gets there. But a lot of times, if you've waited till that storm is knocking on your doorstep, you really have risked it a little bit, because lightning can strike out well ahead of a storm. So if it's loud enough to hear thunder, then you're loud enough to be struck by lightning. So we always tell folks go indoors. And again, just a quick look at those Indiana stats. One that sticks out there again is 2012, the Henryville EF4, along with a couple other pretty strong to violent tornadoes. Again, tornadoes can on any given year be more of a killer, but still overall, flooding is the bigger threat. So wanted to hammer that home. Want to talk a little bit and just review, why do we need storm spotters? And the reality is, we have tons of weather data, we have satellites, we have radar, and a lot of times we have a pretty good idea of what's happening in a storm, but we really won't know a lot of times what's happening on the ground. So we need that ground truth. Again, we can have a pretty good idea, but until we hear from somebody that's actually visually seeing what's happening, that hurts our confidence a little bit. So for instance, let's just say, we've got a storm that's rotating pretty strong. We've got a tornado warning out on it, but all we can put on that warning is radar indicated. And so if you think about from a media perspective, if the media is trying to communicate this threat to the public, there's a big difference between the media being able to say, we have a radar indicated tornado that's heading towards your town versus we have a confirmed tornado on the ground. So, people are most certainly going to react more to that. We have a confirmed tornado and it's heading your way than it's a radar indicated one. So if we can get a spotter report of that tornado on the ground, that's very helpful. That's huge. And that really helps the messaging from our perspective and from the broadcast media, who do an excellent job at conveying that message, and getting people to react to those warnings. So, so what do you report as a spotter? Hail is obviously important. The smaller hail, we still kind of want to know about it. But really, once you get to an inch or greater in diameter, which is the same size as a quarter, that's what's considered severe. And so, yeah, use these references that we have listed here. Basically, quarters are your severe threshold. Golf ball sized hail is getting to be pretty serious. That's going to cause some damage to roofs, windshields, cars, things like that. And then when you're getting into, baseball, tennis ball, softball, that's pretty rare around here, but we can get it. We've had some supercells that have produced baseball to softball sized hail. So it's not out of the question. One thing I'll say about small hail, try to avoid using the word marble because they come in all different sizes, and a lot of times we don't really know what that means. So, compare it to a pea or, maybe to a penny or a nickel, which is all just a little bit less than an inch in diameter. That's usually a little more helpful. Also, when you're reporting hail, try to report the largest stone that you see. That way we know just how big that hail got. We talked a little bit about wind and flash flooding. Wind, any uprooted trees, that's usually a wind strong enough to produce severe damage, which is 58 mile an hour or 50 knots. Damage to buildings, sometimes is probably more like the 60 to 70 mile an hour plus range. Power lines down, that's all stuff we would like to know about. Flash flooding, same thing. If you come across an impassable roadway, you'll want to report that. Number one, especially if it's dark, because if folks are driving along in the dark and they can't see that a roadway is flooded, they could drive right into it. So it's good to let authorities know, that way they can block that road off. And also we need to know about it so we can issue flash flood warnings or compare that to how much rainfall has fallen to help us make decisions. So all good stuff there. What do you need to report and where and when? So photos are preferred. Obviously that helps, kind of take any doubt out of any equation. It's hard to argue with a photo. Tell us, where you're located very specifically if you can. Street intersections are good, or latitude and longitudes even. It's very helpful. The exact time that it happened, or an approximate time if you have that. A lot of times we can match up a report with radar, so the time, if you can get us in the ballpark, we can usually match that up with radar pretty well. And then, what's occurring? Is it hail? Is it wind damage? Are you seeing a funnel cloud? Are you seeing a tornado? That sort of thing. How do you support information, or how do you report information? through Facebook and Twitter. We are on social media, so Twitter is at NWS Louisville. I got the handle there written down, and then Facebook is U.S. National Weather Service, Louisville, Kentucky. Call your local 911 dispatch and report any significant weather. And here's our spotter number. You can get a hold of us 24/7, 1-800-292-5588. So make sure you write that down. It's also on your spotter handouts. So yeah, that's all good info. And again, all that info should be on your spotter handouts that you can reference at any time. We kind of covered this, so I'm not going to spend a lot of time here, but again, we are on Facebook and Twitter, and again, photos are the best way, or videos if you can get that to us. Just remember, do it safely. Don't risk your life to get a photo or a video. While it is helpful to us, it's not worth risking your life. So, but yeah, those are certainly good ways. What we do is we use that to issue local storm reports, which helps document severe weather events. It also helps us with our verification. We kind of grade ourselves on how well we do with watches or with warnings and things like that. So if we get reports that go along with our warnings, then we know we issued a good one. Or if we don't get any reports and we issued a warning, then that might have meant that we false alarmed a little bit. So then we go back and look at the science of things and see what we could have done better. So they really are helpful. So still in review here, what to report. Tornadoes, obviously, if you see a tornado, we're going to want to know about it. So just some things to remember from basic spotter training. The tornado, basically, that's going to be in contact with the ground. So you should be able to see either a condensation funnel all the way to the ground, or if the condensation funnel is not all the way to ground, look below it at the ground and see if any debris is being lifted or tossed into the air. You can have a condensation funnel that's not full and still have a tornado on the ground. Because after all, tornadoes are just air, and technically they're invisible. The only reason we can see them is because of condensation, because of the lower pressure, and because of dirt and debris that's being picked up. So yeah, definitely try to know for sure whether it's on the ground or not. If it's a funnel cloud, like I said, you may see it hanging halfway down, but if you can't see anything below it, report the funnel cloud, but then keep an eye on it and see if it does start picking up debris. And then maybe after the threat passes, go into that area and see if you can find any damage. A lot of times too, if you stare at it close enough, you'll be able to see if it's rotating or not. So that's all important information. Again, if you've taken basic spotter training, wall clouds are something you should be familiar with. Basically, that's going to be a lower cloud base beneath an updraft base of a thunderstorm that should be rotating. And it's a precursor to a tornado. Statistics are kind of sketchy, but anywhere from about 10 to 20% of wall clouds will produce a tornado. So, and you'll see it rotating about a vertical axis. So in other words, it'll rotate like a spinning top. And I've got some really good examples. I'll show you a great video of a rotating wall cloud. Another thing to go along with wall clouds is shelf clouds, which we're going to cover plenty of that as well. And if you come across any wind damage, like we talked about, down barn, let's say you were out on vacation for a whole week and you come back and learn that, your neighbor said, hey, we had a storm 5 days ago, but you have damage. Just because it's been 5 days, that doesn't mean we don't want to know about it. We still do. So even if it's a delayed report, that is helpful information to us. So feel free to reach out. Okay, so one other thing I'll say about wall clouds too is a lot of times we get some scary looking clouds or scud clouds that hang down low from thunderstorm bases. Just try to make sure that it is rotating before you report a wall cloud. That's probably one of the most commonly misreported features is a wall cloud. People will say it's a wall cloud when really it's just scud, which is just pretty much around for just about any storm. You'll probably find some scud somewhere. So if you aren't sure, just stare at it for a second and see if you can see it rotating. Okay, and we kind of covered the hail, but just wanted to kind of remind you that really the best way to do it if you are going to send a picture of hail is to put it in reference to something. So if you have a ruler, just put it next to the ruler so we can see the diameter right there for ourselves. Or say it's the size of a golf ball, hold up a golf ball with that hailstone so we can kind of compare the size. Every once in a while you'll get somebody with a giant hand that's holding a hailstone, and you think, gosh, that hand really big, so maybe that's a giant hailstone, but sometimes things get lost in the reference a little bit. So it's best to have an object to compare it to. And, I think we covered the flooding pretty well. So just again, if you come across some sort of flooding, be sure to report it because you could help somebody down the road that's going to encounter that flooding, especially at night. Um, so moving on here, and we're still kind of in the review phase, but we're getting ready to move into the more advanced stuff here in a second. So, you kind of want to just cover, well, why do I need to report all this stuff, or why is it important? This stuff doesn't happen very often. And the reality is here in central Kentucky, southern Indiana, in our region, we kind of have, how if you think about the Great Plains, their severe weather season is most of the time confined to kind of your mid-spring type months. And it's kind of a fairly short season. For us, we can get severe weather any time of the year. Every month of the year, we can get a tornado or some sort of damaging wind event. So, even though we aren't the classic or typical tornado alley that everyone's kind of familiar with, we certainly get our share of severe weather. And just kind of a climatology that was done, we're somewhere between 45 and 55 thunderstorm days, in a year, and that's about 12 to 15%, of your year. So now, not every one of those days produces severe weather by any means, but just on average, about 1 in 10, or even maybe one in 8 or 9 days, you'll have some sort of thunderstorm type of event in your region. All right, so kind of covered some of the basics here. So let's get into thunderstorm ingredients and how they develop, and then go from there. So there are 3 different types of ingredients that you need to create a thunderstorm. The first one's moisture. You're also going to need some sort of lift or a triggering mechanism. We'll get into that. And then finally, you're going to need instability or fuel, or tape, like we've talked about a little bit already. So let's talk about moisture here for a little bit. Us being in the Ohio River Valley here, we've kind of got a pretty cool setup where we've got the Gulf of Mexico, which is really kind of a main moisture source for a lot of our storm systems. If you think about it, surface low pressure areas, they'll develop, to the east of the Rockies out over the southern or central plains. And then a lot of times they'll kind of track up through either the mid-Mississippi River Valley, say, the St. Louis area, and then up into the Great Lakes, or even sometimes they'll track over us or to the south of us. But if you think about counterclockwise flow around a low pressure area, that basically brings your moisture source straight from the Gulf of Mexico. So, as that low is tracking up towards the Great Lakes, it's just drawing moisture up from that, that source region. And in addition, whatever storm system has spawned that low pressure system, a lot of times you've gotten at least some Pacific moisture out of that system as well. So not only are you getting a good source from the Gulf of Mexico, but you probably already had at least some existing moisture from the Pacific Ocean. And in rare circumstances, you can maybe even draw on Atlantic moisture a little bit as well. So really, for us here in the central United States, there's no lack of moisture. In other areas, other parts of the country, or even parts of the world, based on your geographic location, a lot of times, you may not have that really perfect moisture source region. So you don't see the type of weather that we see here. And I'll even use Kentucky as an example. So, and this is kind of just a general statement, but the further east you get into Kentucky, if you think about the Appalachian Mountains, the chain there, and you need the fact that you need southerly flow to bring moisture up into our area, a lot of times the mountains can actually block or dam that moisture on the eastern side. So, eastern Kentucky can still get severe weather, but a lot of times, you don't quite have as good of an environment the further east you get, and the Appalachian Mountains can play a role in that. So kind of just a local example there, but definitely here in central Kentucky and western Kentucky and Indiana, just given the way that the storm systems move, you certainly have good moisture source regions. And we also mentioned the Great Lakes as a little bit of a limited source region. Most of the time that's more for, lake effect or lake enhanced type snow bands, or occasionally we'll get like northwest flow snow showers from fetches of moisture off the lakes. It doesn't probably play a huge role in our severe weather a lot of times, but it could probably play a small role in some very localized focused boundaries that storms could initiate on, or little mini cold fronts or warm fronts, if you want to think of them that way. But for the most part, it's the big bodies of water we're talking about here. All right, so moisture was our first ingredient. The second ingredient is basically you need lift or some sort of triggering mechanism. And so what do I mean by that? All right, so for any of you who have ever been up in a small airplane on like a warm summer day, you know, what you get is the sun alone can heat the surface. And once you start to heat that surface, you get little air parcels that start to bounce around, because as you warm those air parcels up, they become more buoyant. So if you've ever flown in a small plane, you can get bumped around pretty good. So that's one way to lift an air parcel. Another way is from different weather features that you've probably heard of, like cold fronts, warm fronts, even jet streams. So like little disturbances within the jet stream we call short waves or impulses. So those are also ways that you can provide larger scale lift across the atmosphere. And really, a lot of times these air parcels, all they need is a little bit of a nudge to really get going. So let's kind of just give you an example here. So this would be like a cold front. Let me let this play through here. This is kind of how a cold front can act as a triggering or a lifting mechanism. And what a cold front is really, it's just a wedge of cold air that's riding across the ground, right? And the reason it hugs the ground is because cold air is more dense than warm air. So basically it acts as a wedge, and it will force those air parcels up higher than they would have gone. And then what happens to an air parcel is, as you lift that air parcel, remember that the temperature cools with height, right? We call that a lapse rate. It's the same reason that, you know, there's snow on the top of the Rocky Mountains still in the middle of, well, late May, early June, you know, even though it's very warm on the ground, you still have snow up there. One, because they got more snow probably during the winter, but two, because it's much cooler aloft that high up. So as that air parcel rises, it cools and starts to condense. And then once it gets to a certain height that it's become saturated, that's when you start to get clouds. And, you know, and then if there's enough building from there, you can actually get precipitation. So that's what you need. You need your moisture. And then you also need some sort of lifting or triggering mechanism, like a cold front, warm front, you know, some sort of disturbance in the jet stream, that sort of thing. And then the final ingredient, and this is kind of the most interesting of all of them, and we're going to spend a lot of time talking about this instability or fuel for the thunderstorm. So what do I mean by that? And so you all have probably heard kind of when folks talk about storm systems and getting, you know, warm, moist air meeting, you know, cold, dry air, and that creates thunderstorms. And, you know, that's a very broad and general way to characterize it. A lot of times people don't talk about the depth of that warm, moist air versus the cold, dry air. Really what you need is you need warm, moist air at the surface and in the lower levels of the atmosphere, but you need that cold, dry air aloft. So you need that above that warm, moist air. And again, we're going to get into why that setup is what creates an unstable atmosphere and why thunderstorms then develop and thrive in that type of environment. Before we get to that, though, I wanted to mention that if you have a setup where it's the other way around, let's say you have the cold air at the surface and then you have warm air aloft, kind of above you, that's actually a limiting factor for any sort of thunderstorm development. That's actually a stable layer. And so another word that we use for it is a cap or an inversion. Slides. Okay, so somebody's saying that I'm not sharing the slide presenter screen. It's not the full screen itself. So let's see here. I don't know how to change that. Sharing. Give me 1 second here and I'll see if I can make that a larger version. Well, I don't want to mess that up. Hopefully y'all can still see the screen. I'm not sure why it's not sharing in more of a larger view, but I might try to fix that at the break. But anyway, moving on here. So again, you need that cold, dry air above the warm, moist air. And again, if it's the other way around, if you have a layer of warm air above you, that's actually going to act as a lid or a cap on thunderstorm development. And we're going to go into a lot more detail about that. So again, what you need to think about with respect to instability are these little air parcels or these little bubbles of air floating around. And kind of what I want you to visualize, because it's kind of an easy way to explain it. There's actually going to use several analogies. Think about a beach ball at the bottom of a pool. That's one way we're going to kind of view these little air parcels in this buoyant atmosphere. Another way is I want you to think about a pot of boiling water on a stove. That's going to be another analogy we're going to use. And then we're also going to reference maybe just the room that you're sitting in. Think of the floor as the ground or the surface, and then think of the ceiling as like the top of your atmosphere, at least of the troposphere, where the weather occurs. And think of your the room or the air in between those two areas as kind of your environment. So and that's going to be the best way that we're going to be able to describe all this. Okay. So we talked about these air parcels and rising and instability and all that, and you're like, well, what does all that mean? So let's get into more detail here. What actually causes an updraft? So from thermodynamics, what we know is that an air parcel that's warmer than its surroundings is going to continue to rise until it's no longer warmer than its surrounding air mass. Okay. So, and if we already know that air cools with height, right? We already talked about lapse rates and snow being on top of a mountain even during the summer, or at least the early parts of summer. We know that. So if you think about an air parcel that's rising from the ground and getting higher, it's actually going to continue to a lot of times stay warmer than its surroundings because the air cools with height. So that causes that air parcel to be buoyant or continue to rise. All right, so let's just talk about this pot of water for a second. So you set, say, a room temperature pot of water on a stove, and then you start to heat it up. So what's going to happen first? Well, you're gonna heat the bottom of that pan up first, and so that surface, the bottom surface of that pan or the water right near the bottom is actually going to be the first part that heats up. And if you've ever noticed while you're boiling water, you'll start to get little bubbles on the bottom, right? So think of those as our little air parcels near the surface that are starting to float around. And then as you continue to heat that, some of those little bubbles will start to rise, okay? And what's happening there is those little air bubbles are getting warmer than their surrounding water, and they're becoming buoyant and they're rising. So another way you can look at it again is a beach ball at the bottom of the pool. Basically, you'd hold that beach ball down at the bottom of the pool, and just imagine it's basically a less dense or a buoyant thing. And when you let that beach ball go, it's going to rise rapidly through that water and actually, shoot out the top of the water. So kind of a perfect analogy really are those two things. So let's continue on here. The warmer the parcel is compared to its surroundings, the more it's going to expand and become less dense, like we talked about. And so the faster it's going to accelerate vertically. So if you think about that beach ball again, a larger beach ball is actually going to rise faster than a smaller beach ball because it's even less dense and it's more buoyant. So that's a little experiment you can try. And again, a pool simulates the atmosphere almost perfectly when you're thinking about convective principles like we're talking about here, or unstable principles. So I just want you to remember through all this though, that any sort of warm layer or inversion that we've talked about, that's going to limit the rise of that air parcel, because again, that air parcel wants to be warmer than its surroundings. It doesn't want to be the same temperature or even cooler than its surroundings. It's definitely not going to rise in that scenario. So if you've taken basic spotter training, we've talked a lot about anvil clouds and overshooting tops at the top of a thunderstorm. And we're going to get into great detail about why those form. And it's really pretty cool stuff. So let's quickly review the thunderstorm life cycle so that we can continue talking about updrafts and instability. So there's three main stages to the thunderstorm life cycle. The first stage is that developing stage. So again, we got our air parcel that's rising. It's basically cooling at a certain rate as it rises. And then as it's doing that, it's starting to condense, and it develops into either towering cumulus or eventually a cumulus congestus. Now, it's not a thunderstorm, or it's not a cumulonimbus until it starts to produce precipitation, which is the second stage here. This is the mature stage of the thunderstorm. So once you have this updraft that's risen high enough and started to condense and started to precipitate, it will then produce a downdraft. And when that happens, that's when you actually have a full-blown cumulonimbus or a thunderstorm, however you want to characterize it. That's when you have an updraft and a downdraft, and it's actually precipitating. And this is where you get your, your features of the storm that we talked about in basic spotter training. You get your updraft, you get a really nice anvil cloud at the top of the atmosphere there, and sometimes you even get an overshooting top. And then, of course, you can get a pretty mature downdraft. And then the third stage is the dissipating stage, which is when that thunderstorm collapses. So, that thunderstorm is going to maintain itself as long as that updraft can maintain itself. Sometimes in environments where you don't have a lot of wind shear, if that updraft goes straight up, then the precipitation from that storm is basically going to fall right back down on that updraft, and it's going to choke that updraft off pretty quick. But if you actually have wind shear, which will tilt the updraft, you can sustain an updraft for quite a bit longer. So again, we're going to get a lot into wind shear as we go through this and why that drives certain storm modes. But the bottom line is once you lose your updraft, then you're going to become in the dissipating stage of the thunderstorm cycle, and that's when you've got nothing left but a downdraft. So the storm's going to rain itself out and maybe blow itself out as it collapses, and then that'll be the end of the storm. Okay, so now that we know that, let's move on here, and let's get into some of this pretty detailed stuff here. All right, so I wanted to talk more about this instability and how we actually see this and how we actually forecast this. Okay, so what you're looking at here, and we're going to spend a lot of time on this slide, so don't panic as we kind of digest this here. So what we're looking at is actually a thermal profile and it's actually a moisture profile as well of the atmosphere. Okay, and so if you look at the bottom of the screen here, this is basically the surface down here, where you see basically all the numbers, the temperatures in degrees Celsius. Okay, and then if you go up to the top of the graphic, this is basically the top of the troposphere, which is where all weather occurs within our atmosphere. And so we're talking, depending on time of year, you're 40, 50, 60,000 feet up in the air when you're up here this high. Okay, so this is kind of the depth at which weather occurs in. All right, so what you're looking at, and if you've ever heard of weather balloons, we launch weather balloons to kind of get this type of data. What you're seeing here, this red line is the temperature of the atmospheric profile. So here's what the temperature is at the surface down here, and as you go up in height, this is what the temperature does. So if you noticed, because we have a temperature scale down here, it shows you basically, 0 degrees Celsius is freezing, minus 20, 10, 20, 30, 40, and then, 10, 20, 30, 40 on the positive side. So what's happening with height is that temperature's cooling, like we talked about, right? You can see the red line. Okay, this other green trace is your dew point at those same heights. Okay, so anywhere where you have a temperature and a dew point close together, that's where your atmosphere is more saturated, and you can have cloud layers in those areas. So here and here would be good examples of that. So if you remember, what we want is basically a situation where your rising air parcel is warmer than its surrounding air mass. Okay, so when the air parcel is in the lower levels, so near the surface up to maybe 3,000 or 4,000 feet, a lot of times it's going to rise at something we call the dry adiabatic lapse rate, which is kind of a standard rate of cool, and that's about 5.5 degrees Fahrenheit per every 1,000 feet. And the thing about this lapse rate is this is only going to happen. It's only going to rise and cool at that rate until it becomes saturated. So usually when you get up around 4,000 or 5,000 feet, that's when you've cooled the parcel enough to become saturated. And then once it becomes saturated, it's actually going to cool at a different rate. And that's why you see this dashed line here. That's why it changes direction. Is basically that's your moist lapse rate versus your dry lapse rate. Okay, so this air parcel is floating around down here. It's starting to warm up the surface. It starts rising. As long as it stays warmer than its surrounding air mass, which is this red line, it's going to continue to rise. Okay, so what you'll notice about this sounding, and I'm just using this as an example, is that this actually has some warm layers in it, so some caps, some inversions. So this sounding technically would inhibit thunderstorm development. Now, if you could get the air parcel up here to where your dashed line is to the right or warmer than your environmental temperature, then that parcel is going to rise on its own. And that's called the level of free convection. But again, you need some sort of trigger or something to get that parcel that high. So we're going to go through several examples here. But the bottom line is, you have to look at a sounding to know what kind of potential instability you have. And again, it's going to basically be anywhere where your air parcel is going to rise warmer than its surrounding environment. But there's also places like caps that you have to look for that will inhibit convection. Okay, so let's take a look and kind of look at this again from a different perspective. All right, so anywhere that line, the dotted line, is warmer than your environmental temperature, the red line, you're going to have what we call CAPE, or convective available potential energy. Again, that's potential energy. That doesn't necessarily mean you're going to be able to tap into that. Like I said, you have to get that parcel high enough that it will release on its own. In other words, it'd basically be like letting that beach ball go at the bottom of the pool. So again, there's several ways to do that with cold fronts, warm fronts, or just pure surface heating alone. And what we do is we actually measure that in units. So basically, we're measuring that area where you have that instability, and then we're assigning values to that here. So basically, it's kind of measured in thousands of joules per kilogram, which is an energy unit. So that's kind of how we see instability. So let's look at this from yet another perspective. Okay, so what's happening when that air parcel is buoyant and rising is it's accelerating. Now, wherever you have a really wide gap between your air parcel temperature and your environmental temperature, the wider the gap, the more it's going to accelerate. So you're going to have really strong accelerations in these mid levels. So you're up here, you're around 15, 20, 30,000 feet. That updraft is really accelerating, but it's going to be traveling its fastest when it gets up here to the top of our atmosphere. And you'll notice what happens up here is suddenly you run into a layer of warm air aloft. That's always going to be there. That's called the tropopause. And so that's why thunderstorms don't just keep going. They don't just keep rising up into outer space. They're actually hitting a layer of warm air aloft, another cap basically. But again, we're up to 40, 50, 60,000 feet here. So if you want to go back to your analogy again, think about if you're sitting in your room, if you let a balloon go and it rises, goes up and hits the ceiling, exact same thing. That's hitting the tropopause up there. And so then if you think about all that energy that's rising in an updraft and gets up and hits that ceiling, what's it going to do? It's not just going to stop. What it's going to do is it's going to spread out. And that's how you get your anvil aloft. So another thing that happens with a thunderstorm, and you've heard us talk about this if you've been in a basic spotter training, is an overshooting top. And so again, that updraft at this point, when it gets up here to this equilibrium level, if it's a really unstable and a really strong updraft, it's going to be going 80, 100 mile an hour in some of the strongest storms. So there's so much momentum that it'll actually overshoot that equilibrium level or that ceiling or that cap. And that's why you see that little bubble on top of a thunderstorm. So that is an indication of a very strong updraft, and that's what's happening. So again, going back to our analogy with the pool, when you release that beach ball from the bottom of the pool and it rises quickly up through the water, it doesn't just stop as soon as it hits the top of the water, does it? No, it actually shoots out of the water a little bit and then settles back down. So, and that's exactly what's happening with an updraft of a thunderstorm. And it actually creates then shock waves. And we've seen in satellite imagery and high resolution satellite imagery of an overshooting top popping out of an anvil, and then you'll actually get gravity waves or shock waves on top of those thunderstorm anvils that spread out. And if you're flying an airplane up there, you don't want to be anywhere near that because that can be severe turbulence. It also actually can even manipulate the environment to the point where it can trigger new thunderstorms with those gravity waves or those shock waves, because we're talking about energy release on a pretty large scale there. So really what I would just want to remember here is that anywhere, your updraft is going to accelerate the quickest wherever you have these larger fat areas between your parcel temperature and your environmental temperature. But again, your fastest speed is going to be at the top because it just continues to accelerate, all the way up. So hopefully that makes sense. All right, so now let's apply that to an actual thunderstorm that we're looking at from a distance. And you'll be able to see everything that we just talked about right here in this image. Okay, so let's talk about this from the beginning. Let's start off and imagine our little air parcels that are, floating around down near the surface, in the lowest couple thousand feet. Again, you can't see those air parcels yet because there's no condensation yet. They haven't saturated to the point where they're moist, okay? So if you're flying in an airplane below this cloud base, you're gonna be bouncing around like crazy, right? Because those little air parcels are bouncing around everywhere. You just can't see them. We're not gonna be able to see those air parcels until they saturate. And again, the height that occurs is gonna be what you would call your cloud base, or your LCL, which is your lifted condensation level, okay? And that's gonna vary in height based on how much low-level moisture you have. So if you have a pretty moist low level, then your LCL is gonna be pretty low because it doesn't have to rise and cool very much to get to its saturation point. But if you're in more like a drier climate out west, then some of those bases are gonna be really high, maybe 6, 7, 8,000 feet or even higher. So again, it kind of depends on your environment. One thing I'll say about LCLs, it is an important parameter for tornadoes. You really need pretty low LCLs to have tornadoes. Generally 600 to 800 meters is ideal. Once you get to 1,000, 1,200 meters, you can still have tornadoes, but a lot of times they're going to be more of the ropey variety, the skinnier ones. If you're talking about wedge tornadoes, violent tornadoes, usually your LCLs are in that 600 to 800 meter range or lower. So that is an important parameter to pay attention to. So, okay, so we've got to the point where, our parcel has saturated. And again, now that parcel is going to rise and cool at a different rate than it did from the ground up to that cloud base. And this is where that parcel can suddenly get released into convective, into that convective energy, that potential energy that we talked about. Because again, it's going to cool at a pretty slow rate. Meanwhile, you're getting up into the mid and upper levels where you get some really cold air aloft and you get really quick lapse rates with your actual environmental temperature. So this is where that parcel is really going to accelerate quickly. And you can actually see it in the clouds. You can visually see, if you see this rocky, hard, kind of cauliflowery, knuckly type formations, those are indicative of a very strong updraft, okay? So here you're rising from, let's just hypothetically say 10,000 feet up to 30 or 40,000 feet. Again, we're staring at this storm from probably 30 or 40 miles away, so it doesn't look very high, but that's, at least 20, 30,000, maybe 40,000 feet in depth that we're looking at right through there. And again, that parcel is accelerating very quickly through this layer. And then it gets up to the top of that equilibrium level that we talk about, and it runs into that strong layer of warm air aloft. And again, you got all that momentum that's going fast. It's, at its fastest speed up here, and it runs into that cap or that lid or that ceiling, and it has nothing to do but then spread out from there. And of course, again, you have so much momentum that you are going to overshoot that a little bit just because of how fast that updraft is traveling, and that's why you get your overshooting top. Again, the analogy for that is your beach ball coming up out of the water when you release it from down below. And again, you see your anvil, and that anvil will basically spread out in the direction of your upper level winds. So you can actually kind of tell what your steering winds or which way that storm is going to travel based on which way that anvil spreads out. Now, sometimes you can get a back sheared anvil, which will actually spread out backwards towards your upper level winds. And that's just another indication of very strong updraft. If you think about a salmon swimming upstream, if an anvil is able to spread out backwards towards its upper level winds, then you got a pretty good updraft in that situation as well. So I know that was a lot to take in, but I kind of wanted to just really go through that, and so you kind of understand what you're looking at when you're looking at a thunderstorm, and you understand how instability plays a role in those air parcels rising, and what actually can release those air parcels. So I know we've talked about a cap a lot, so I just wanted to show you one more example. Again, this is a sounding that shows what would be quite a bit of available potential energy. If you look in the upper parts, the mid and upper parts of that sounding, some pretty good fat area between your parcel temperature and your environmental temperature. But look, if your air parcel is rising right here, you can see it suddenly gets warmer with height through about a 2 or 3,000 foot layer. That's a cap. So you've got to find some way to break that cap. whether it be with, some sort of lifting mechanism like a cold front or a warm front, or with heating alone. But again, you are not going to get a full-blown thunderstorm until you break that cap. You'll get clouds to rise up to that cap, but then they won't go any higher. And one thing I hadn't mentioned yet about these soundings, you also get wind profile data throughout the height of that storm, or that atmospheric profile. So you can see these little wind barbs over here on the right, and it shows you which way the wind blown and how strong it is. So that's how we gauge how much shear is in the environment as well, which we're going to talk a lot about shear later. All right, so continuing on with the cap. And you'll get meteorologists talking about a thunderstorm day, and they'll say, we could have severe weather today, but we don't know whether that cap is going to break. Sometimes the cap is just strong enough to where it'll hold things in place all day and you just won't break it. Other times it's there, but it's not that strong, and you think there's a chance that you could break it. So, sometimes there's some uncertainty. We call that kind of a conditional threat. It's like, yeah, if thunderstorms do form, they can be severe, but we just don't know if they are because we don't know if that cap's going to break. The good news as a spotter is you can there are visual clues that tell you if that cap is potentially breaking. And that comes in the form of a pileus cloud. Sometimes I pronounced it pileus, but I think it's actually pronounced pileus. And what it is it's this cobwebby, really smooth cloud that will form on top of a developing cumulus cloud. A lot of times it's a cumulus congestus or a towering cumulus. You'll see that. And what that is that's basically that rising air parcel, that cooling, condensing rising air parcel ramming against that cap, and it's actually trying to mix it out. And you'll get really strong winds. You wouldn't want to be flying an airplane anywhere near something like that, because that would be incredibly turbulent in that area. Now, again, some days that may just pound on that cap all day long and never break it. But if you watch it close enough, and there's nothing, in all my storm chasing days, the coolest thing I've ever seen is just explosive development of a thunderstorm after it broke the cap. So you just got to watch and see if it starts to, tear through that. And then sometimes it'll look like it broke it, and then you'll think, okay, here we go. We got storm initiation, and then the storm will just kind of gradually weaken. Even though it broke through, it just didn't make it beyond that because it didn't truly, really completely overcome it. So again, just watch for those very smooth and striated clouds on top of a developing cumulus to know if that updraft is actually working on or trying to break the cap. This picture on the on the left is pretty interesting. It's actually, I'm pretty sure it's a pyrocumulus that's developing from a forest fire, and kind of crazy to see that a forest fire created, an updraft that strong. And actually, if it broke the cap, then you can actually get a full-blown thunderstorm over top of a forest fire, which, on one hand, you can maybe say it would be good that, you're getting rain on a fire, but on the other hand, you get gusty winds with that can make a fire worse in situations. So pyrocumulus and pyrocumulonimbus is a kind of a crazy phenomenon, but just an overall pretty interesting picture. All right, moving on. So we talked about those soundings, and again, we launched those weather balloons across the country, several different sites across the country, 2-3 times a day. We even have aircraft that fly around and take atmospheric soundings as they're flying through the atmosphere. So if you're interested in that type of thing, like I said, you just look at a sounding, you can really gain quite a bit of knowledge about what you're looking at with the atmosphere. Here's a link to copy down. And again, tomorrow might be a great day to kind of follow soundings and see what you're seeing in the environment based off what you learned today, and kind of experiment and see if you can kind of apply what you learned. So I'll give you a couple more seconds to copy this down. And again, it's the Storm Prediction Center website, which we're going to be hitting that a lot as we go through this presentation. Okay, so we talked about all that CAPE and that instability and that fuel for thunderstorms. And we talked about some numbers that get assigned to, again, how much positive area we call it, within that sounding is actually truly available energy. And so we'll assign a number to that. And in general, the higher the number, the more unstable it is. If you don't have any CAPE, so in other words, if that air parcel is not warmer than its surroundings anywhere throughout that thermal column, then it's basically considered a stable atmosphere, and you're not going to get any thunderstorms in that environment. But your lower values, 100 to maybe 1,000, is generally pretty pretty lightly or marginally unstable. And then if you're getting into, 1,000 plus up to 2,500, that's considered moderately unstable. 2,500 up to 4,000 joules is considered strongly unstable, and then anything greater than 4,000 is what we'd almost consider extremely unstable. But the thing you got to know about this is kind of season dependent. So, right now we're still in the cool season, and we get a lot of cool season type of events around here. And in the cool season, because you have so much wind shear and wind energy and strong forcing from the storms that create these environments, you can get by with a lot less instability. So in a cool season type of event, 500 to 1,000 joules of CAPE is really quite a bit, especially if you have a ton of wind shear. But once you get into the summer months, you don't have nearly as much wind shear, and so 500 to 1,000 joules is not much at all. That's considered weakly unstable. So really, it's seasonally dependent. And what you're going to see with tomorrow's event, at least for our warning area, around the I-65 corridor, give or take 50 miles on either side, we're only going to probably have a couple hundred joules of instability. And so the big question with that event tomorrow for us being farther east is are those, is there going to be enough fuel for those storms to survive? And again, we're going to get into some of that data at the end of this talk. Now further west, they have even more instability, and again, given the amount of shear, it's probably going to be more than enough that Western Kentucky and especially the Missouri Boot Heel and all those areas that are in the higher outlook are going to have some problems tomorrow. Okay, so we've talked about some of these parameters and things that we look at. And again, as part of the advanced spotter talk, I feel like if you're taking an advanced spotter talk, you're interested in weather, or you're interested in becoming more interested in weather. So I wanted to give you some tools to really kind of look at this stuff yourself, because it's out there, it's available to the public, and you can learn a lot from looking at this stuff and then applying it to what happens with each event. So the Storm Prediction Center, it's www.spc.noaa.gov, out in Norman, Oklahoma. If you click on their main homepage, and then if you see where I have the black arrow, it says Meso Analysis. If you click on that, you can actually look in real time at this instability hour by hour. This will update hour by hour, and it'll assign values based on, you don't actually have to analyze the sounding like we did earlier, and see the air parcel and all that. It'll just give you the numbers, and so you can see where the most instability is pooling and things like that. It'll also even tell you where the environment's capped. So this blue shading that you see is actually capping, which would limit thunderstorm development to some degree. Now I will say you can click on thermodynamics, and there's going to be there's actually going to be 3 different types of CAPE. Really the one that's going to be most representative most of the time is mixed layer CAPE, or ML CAPE. Some of the other ones are used for different environmental purposes, but in general, mixed layer is probably going to be your most representative value. And you can actually read, there's little question marks by each parameter. You can actually read more about them if you click on them. So anyway, I just wanted to kind of show you that is available to you. And again, take a look at it tomorrow and kind of follow along with tomorrow's event and see what you can see with respect to what you learned today or this evening. Another thing about the Storm Prediction Center is we talk a lot about these convective outlooks. I think I showed them at the beginning when I did a little briefing about tomorrow's event. So they're going to basically every day, and these get updated several times a day, from day 1 out to day 8 actually. They're going to update where your best threats for thunderstorms, so even just general thunderstorms that aren't expected to be severe, are in this light green, and then your marginal environments are in the darker green. And then basically as you get into yellow, orange, and red, and even purple if it's a high risk day, that's when you're getting into your more serious type of weather threats. So, and it's basically kind of like your traffic light, green is okay, most of the time it's not going to be a big deal. Yellows, hey, you might need to use caution, this could be a little more serious. And then obviously red and purple are pretty bad, and those kind of in general are pretty alarming colors. So you can also think of it as like a level 1 through 5 type of scenario if you want. So just to kind of give you an idea, marginal actually can mean 2 different things. Marginal can mean 1, and we'll just use a cap as a good example. 1, it could be, hey, if the cap breaks, we're going to have severe weather today, but we don't know if that's going to break. So it's kind of a conditional threat. Or it could just mean that, hey, storms are just going to get strong enough to maybe produce like a couple of quarter-sized hailstones, or maybe a 50 to 60 mile an hour wind gusts, just your kind of baseline, barely severe type of a threshold. Once you get into the slight risk or level 2, that's when you're talking about, you're expecting that you are going to see some severe weather within that risk area, but it's just not going to be that widespread. And, for the most part, it's going to be, your 1 to 1.5 inch hail, maybe your, 60 mile an hour wind gust here and there, whatever. Usually not too terribly impactful. And then, for instance, once you get into enhanced, which, that's actually Western Kentucky has a good part of an enhanced risk tomorrow, level 3 out of 5. That's when you're talking about your potential for some more significant wind events, more widespread damaging wind events, larger hail, even a tornado threat too, which you can get a tornado in any one of these categories, but in general, your tornado threat increases, the higher your category. So sometimes I don't necessarily like the wording as much as I like the colors, because to some people, moderate, which is a level 4, actually doesn't sound as bad as enhanced. So look more at the color. But a moderate risk, you see one of those, that's a pretty big day. And actually we have one out over Western Kentucky tomorrow and parts of Illinois and Iowa, I believe. You're gonna maybe get 2 or 3 of those in general on average every year across your area. Now, if it's an active year, you may see more. There may be some years where you don't get any moderate risks, but they don't come around very often. So you better pay attention if you're in that, moderate or level 4. A high risk day, that's going to come around less than 1 time per year on average. That's the big deal. I think the last time we were in a high risk here in Central Kentucky and Southern Indiana was March 2nd, 2012. And we know what happened that day, an EF4 tornado across Henryville, and then we had the West Liberty tornado later on that evening. So yeah, that's like tornado outbreak type stuff, or just an incredible derecho type of event, widespread damaging wind event. That's what you're going to see with a high risk. Those are the type of deals where you get people shutting down schools and things like that. So no joke. I'll kind of talk about a recent event, December 10th, 11th, 2021. Since that was in December, which was climatologically probably the least active month of the year with respect to tornadoes, it didn't probably get as high of a risk as it should have. Now, it was a moderate risk out over Paducah's area, and I think it was an enhanced, maybe touching moderate in our area. Had that been a warm season event, we probably would have had higher risk, but sometimes, again, that instability, you just don't know quite what you're going to get out of it. But that ultimately ended up being like a mid to late spring air mass that got in here in early December, and that's why it was as bad as it was. So just kind of interesting to look at these outlooks, and like, again, you can learn a lot just from looking at these and reading these discussions that the Storm Prediction Center puts out. They get pretty technical with respect to the meteorology, but if you look at them and read them enough, you can pick up on a lot of some of the terms. And again, looking at some of the tools that we're giving you here this evening, you can really learn a lot and make yourself pretty dangerous with respect to knowledge about weather, and specifically severe weather. All right, so moving on here, awareness. So within those outlooks, then they'll break it down by category. So you can look at your damaging wind threat, or even your tornado threat, or your hail threat. And what it is it gives you a probability of seeing some sort of damaging wind, tornado, or hail within 25 miles of a point. So it's not saying there's a 30% chance you're going to see damaging wind. It's saying that somewhere within a 30-mile radius of you, there's a chance you could see damaging wind. So that's kind of the way that's characterized. And I know the Weather Channel uses the Torcon. It's a similar type of thing, only I think it uses like a 50-mile radius rather than a 25. And then if you happen to see a hatched area within those outlooks, that means there's a chance of a significant event. So if it's in respect to tornadoes, you could get an EF2 or higher, or if it's with respect to hail, it's 2-inch hail or higher, or with respect to wind, it's like hurricane force wind or higher, which is 74, 75 mile an hour basically. So if you see that hatched area, they're saying, hey, not only can you get severe weather, you can get a pretty high end type of an event. And again, that's all driven by your environmental parameters, how much instability and shear and what type of storm modes we're expecting. So, all right, so moving on here, I think I've already gone an hour, man. Yeah, I'm taking a lot of time here, so I'm going to kind of start to go through these quickly. I've kind of covered some of this already. So back to spotting and looking at clouds and formations and updrafts and potential, eventual thunderstorms. There are some visual clues, so I wanted to teach you some of these. Between these two pictures here, one of these is a much stronger updraft than the other. And I kind of gave you a hint earlier. What you want to look for is the kind of cauliflower, knuckly, popcorny type structure of the cloud. That's going to be indicative of a very strong updraft. So the one on the right, cumulus congestus there, is much stronger, and that has a much better chance of becoming a thunderstorm pretty quickly. The one on the left, it's got good vertical depth, but look how smooth and fibrous the clouds are. That's a much weaker updraft, and that's probably not going to make it. Now later on, maybe if it continues to heat up and get more unstable, you might see it get more impressive. But right then and there, you're not really that close to having a thunderstorm, even though that's got good vertical depth. That's what we call a towering cumulus right there. Okay, so, and we kind of touched on this earlier. We talked about the anvil, why that forms, how that forms. The bottom line is, if you see a very well-developed anvil, then that's a sign of a very strong updraft, because again, whatever updraft makes it up that high and then continues to pump out enough energy that all that mass and moisture is spreading out across the top of the tropopause or the ceiling, if you're thinking about it, your room analogy, then you've got a good, strong, sustained updraft. And within that anvil cloud, look for mammatus clouds. So those are those bubbly clouds that almost look like little balloons or whatever. That's a sign. It's very turbulent up there. You wouldn't want to be near that in an airplane. That's why airplanes try to steer far away from thunderstorms. You'd run into severe turbulence if you got anywhere near a mammatus cloud. Okay, and again, we kind of covered it. Look for that back sheared anvil. So again, if you know which way your storm's moving and you see that the anvil is spreading out to the back towards the upper level winds, then that's another sign of a very strong updraft. Okay, the overshooting top, we covered that as well. Again, that's going to be basically that beach ball coming up out of the water, just because there's so much momentum rising up that it can't stop the second it hits that warmer air. But it then kind of bubbles up and then settles back down. So you see an overshooting top, you have a very strong updraft. Okay, and again, I think we've covered this, so we're going to keep moving on. But those are great pictures, good examples. Again, these storms you're looking at here on these pictures, 30, 40, 50 mile away, some of them. Again, they're 40, 50,000 feet in the air, so you could see, something that's almost twice the height of Mount Everest. You can see that from a pretty good distance. All right, so again, more signs of storm strength. You can actually see the structure of the updraft or the trunk of the storm. And again, you're looking for those well-defined cauliflower type popcorny edges. This one's okay updraft. It looks a little fibrous and smooth, but again, you've got a pretty well-developed storm here. So at one point, it was probably a little stronger. Another sign and potential sign of rotation is some striations. A lot of times you're going to see those in the mid-levels of the storm. If you put a time lapse on that storm, you'd probably be able to see it rotating a lot better, actually. So just looking at some of those features we're pointing out there. The other thing is the rain-free base. So again, this updraft is basically, it's all upward rising air. And again, depending on your wind shear profile, that updraft's going to tilt a little bit if you have any sort of wind shear. And so there's not really supposed to be any rain falling within that updraft. So we call it a rain-free base. You should be able to see that updraft pretty well. In a good, mature, organized storm, that precipitation is actually going to fall away from the updraft. So, if you're standing underneath the updraft base of a storm, you should be mostly dry. But that rain-free base should be fairly dark. In my experience, if it's very sharp, kind of and smooth on the bottom, that's actually a sign of a stronger updraft. That's not always the case, though. Sometimes they can be kind of ragged. But where that basically at your rain-free base is, you're going to get some lower cloud lowerings, basically, or that's where your wall cloud is going to form, because your pressure is lowering there if the storm's rotating, and your condensation level lowers as a result. So you get actually a lowering underneath your rain-free base, and that's where you want to watch for potential tornado development if it's a rotating storm. So again, again, also watch for rising scud or clouds that'll develop below that and then rise up into it. That's a sign of lowering pressure. Strengthening updraft and a rotating updraft is going to cause lower pressure, and that's when your wall cloud's going to form. So if you see clouds rising up into it and getting sucked up into that updraft base, that's a good sign if you're looking for severe weather. So that's a good little tidbit to have. Okay, and then moving on, again, eventually, if the storm is organized enough, you could get a wall cloud. The other thing, like we talked about with your lifted condensation level, how high is that cloud base? If it's a really high cloud base, you're probably not going to want to worry too much about a tornado, but what you will have to worry about is downburst winds, because if you have that much dry air between the cloud base and the ground, that actually gives you more potential for downburst wind energy. So, and again, those lower cloud bases are more favorable for tornadoes. Okay, so another sign of a storm strength. So a lot of those that we just looked at were single cell or supercell type storm structures. Now we're talking about QLCSs or squall lines. So the big identifying feature with a squall line is the shelf cloud. If you've taken basic training, you're pretty familiar with the shelf cloud. This is the one that's going to cover your whole horizon. They come in all sorts of different shapes and sizes and looks. And if you look at these two pictures here, you might ask yourself, well, maybe one of these is stronger than the other. And that one may look more ominous than the other, but the reality is a lot of times you can't really tell. Sometimes you can get some really ragged looking shelf clouds that actually can produce a ton of wind damage. And meanwhile, on the right, you have a really well-defined, very almost, very proper type of a shelf cloud. And you think, gosh, that's really going to produce a lot of wind. And maybe it just kind of comes through with a 30 or 40 mile an hour wind. So you never really can tell for sure, but just know that when you do see a shelf cloud and see it approaching, that is going to signal the beginning of your wind and your heavy rain and lightning. It's basically the interface between your updraft and your downdraft on a linear storm structure. So yeah, sometimes you don't always know, but just be prepared that you're going to get wind and some rain with the passage of a shelf cloud. Something to be careful about with respect to storms, especially shelf clouds, is a lot of times you'll get low-hanging clouds and they look like they could be a funnel cloud, or they look like, really we call these are good examples of scud cloud here. Or, you may be in a place where you have a lot of trees and terrain and it looks like the cloud's hanging down and touching the ground and you think, oh, maybe I do have a tornado. But in reality, you just can't tell for sure. Most of the time with a shelf cloud, it's not a tornado. Every once in a while, you can get a brief spin up tornado, but likely that's going to be wrapped in rain and you're never going to see it anyway. So be careful not to report these types of things as funnel clouds unless you're just 100% sure, or tornadoes, because we do get a lot of false reports in these instances. Okay, and again, just kind of this is again a lot of stuff from your basic spotter training. In general, your shelf cloud is going to cover your whole horizon. It's a much larger feature and it's associated with your linear, squall lines. It's your cloud, the shelf cloud is actually going to slope away from the precipitation. It's an indication of outflow, so you're going to get gusty winds with it. And it kind of moves through the sky like a rolling pin. So you'll see it rolling about a horizontal axis. The wall cloud slopes toward your precipitation core a lot of times. It's actually getting moisture from that precipitation core as well as the lower pressure. It's an indication of inflow into the updraft, and it will rotate. And that's where your tornado will drop out. Again, about 10% of wall clouds will produce a tornado, and it rotates about a vertical axis. So think about that spinning like a top. So here's a really good video of a wall cloud rotating, and you can actually hear fittingly, you can hear the tornado sirens in the background. This was actually in downtown Louisville, or not downtown, but near Churchill Downs back in, I think 2011. We had the Churchill Downs tornado, and this was the wall cloud that produced that tornado. So you can see it spinning really well there. So for the sake of time, I'm going to keep moving along. Other things to watch out for, gustnadoes. So these are not actually tornadoes, but they're a little spin up on the leading edge of a gust front. And so that's the name it's basically gotten, but it is not a tornado. Now it can produce pretty strong, damaging winds, maybe even strong enough to be equivalent to an EF0 or a low end EF1, but a lot of times these can get reported as something other than what they are, and really they are just a gust of wind that picks up dust and debris on the leading edge of outflow. So, again, just be sure what you're reporting, and, kind of pay attention. And I know it gets exciting, or, you get excited if you really think you're seeing something, but just try to be sure before you jump the gun. Make sure it is rotating and really picking up debris if you weren't going to report a tornado. Okay, so gonna keep moving. Man, I'm already an hour, 20 minutes into this. Let's go ahead and take a 5-minute break. I think this is a good place to stop, and then we will get going again right at 8:25, 8:26. We'll keep moving along here. Okay, we'll do about another minute or two here, and then we'll get going again because we've already gone almost an hour and a half. I think we got the screen fixed here now. Sorry about that. I didn't have it on the right display setting, but it should look a little better now. So hopefully you were still able to see those screens pretty well, but if there's anyone we want to go back to at the end and reference, we'll try to do that. I've seen a couple questions come in, and again, I'm trying to keep moving here. So let me see if I can answer some of those while we're waiting for another minute or two. Will the KY4, KY repeater be monitored during severe weather? So we do have a scenario where we have ham radio operators come in every once in a while during the really big events. I'm probably talking like a moderate or high risk type of a day. And they will, because we actually can't, some of us do have ham radio operator licenses, but we can't actually do that while we're on the clock. And a lot of times we're needed to actually work the event. So we will bring in groups to monitor those repeaters for us and then pass along reports. But it's only for the biggest events that we do that. And in fact, I think the last time we probably had that happen was the March 2nd, 2012 event for our area. So So the short answer is, probably not like for tomorrow's event, but maybe somewhere down the line, if we're expecting a giant outbreak, we would have folks in here monitoring those repeaters. But yeah, if you have other ways of getting, if you are a ham radio operator and you get a report, if you want to pass that along through the spotter number, or some ham radio operators are in NWS chat, you guys can relay those reports that way. We would certainly appreciate it. Or just to your local dispatch, that helps as well. So good question there. So yeah, let's go ahead here, and yeah, we're gonna get started again. So I'm gonna turn my camera off. Again, I think we got the screen fixed, so sorry about that for the first part, but hopefully we're still able to see everything okay. This should just be a little less distracting now. So, all right, let's dive into the next part 2 here, and continue on. So I wanted to show you a lot of radar examples, because I know everybody pretty much has a radar app on their phone or some way of looking at radar. And if not, you see it on the TV as well, if you're watching your local news station. And so kind of wanted to give you an idea of what we look at. And hailstorms kind of present a lot of opportunities to see some cool features. And again, we're going to continue to learn about updrafts and downdrafts as we go through some of this stuff. So a lot of the radar displays that you look at are in 2D. You'll just see a kind of a flat picture of radar reflectivities on a screen, and then you watch that move through time. And what you're looking at, basically the brighter colors are the radar bouncing off more returns. So if you have very heavy rain, you're looking at your reds and purples a lot of times, and even the purples and whites can sometimes be hail. And again, that scatters a lot of energy back to that radar, so it paints a higher reflectivity. Usually your lighter precipitation is your blues and greens, and maybe moderate precipitation is your yellows and oranges. But really, if you're expecting hail, what you're looking for is that those purples and those whites. So you see that flat image of the radar on your screen, but really what we have to do is we're interrogating radar and looking at these storms is we have to look at the vertical depth of those storms. We don't just see near the surface, we actually see 20, 30, 40,000, 50,000 feet up in the air. And what we're looking for with respect to hail is really a core aloft, or those really high reflectivities aloft. Because like we talked about with lapse rates, even on a hot summer day when it's 85 degrees out, you get high enough in the atmosphere, 12, 13, 14,000 feet up in the air, you get below freezing. And so all that moisture that gets lifted up in the air from that updraft, that turns into ice particles. And the more those bounce around up there, and the stronger your updraft is, the bigger that hailstone can get. Now, it has to get big enough to still fall through that, 12, 13, 14,000 foot warm layer, so that it's still like, an ice cube when it hits the ground. Sometimes you get, updrafts that are just strong enough to support like little small hailstones aloft. And then by the time it falls through that warm layer, 12, 13,000 feet, it melts before it hits the ground. So there could very well be, hailstones floating above your head, but you may never know it because it never reaches the ground. So what we have to do is kind of judge how deep that warm layer is, or that melting layer. And then we have to see how high that thunderstorm gets above your good hail growth zone, which is your -10 to -20 C, but especially above -20 degrees Celsius. You can get, if you get a storm, a really strong core above that, a lot of times you can get severe hailstones. So that's the type of things we're looking at. And as technology advances and you get more cool software to look at radars, there's different ways of looking at things. So now we can look at thunderstorms in 3D, and that's kind of like being almost out there, spotting the storm. And you can see the same types of storm structure when you're looking at these in 3D. So, I'm not here to really promote any sort of one software or another, but I'll just give you just kind of a couple of examples. This is Gibson Ridge Analyst, so you'd have to pay for a subscription to get it, but you can look at storms in 3D if you do. And a good radar app that a lot of us like to use on our phones. And again, I'm not promoting any one over the other. There's millions of them. Well, not millions, but several of them out there. We like Radar Scope. That's a good one that's going to give you a good display, like a lot of the radar images you're going to see, on this presentation. So, Again, there's several of them out there if you just Google. So take a look and see what suits you best. So some other radar signatures that you can actually see with respect to like a severe storm and large hail, something we call a three-body scatter spike. And really what it is it's a data artifact. What's happening is that radar beam is shooting out through the core of the thunderstorm. And when it bounces into those hailstones that are all kind of oddly shaped and tumbling through the environment, what it does is it scatters that radar beam energy back down to the ground, and then it bounces back up. And so it fools the radar beam almost into thinking that it's seeing more precipitation when really that's just the energy bouncing off the hailstone down to the ground and then back to the radar. So anytime you have a very large hail core and you see a three-body scatter spike like you're seeing shooting out of this storm, that's actually not real. It's just it's basically the radar being fooled. But it is an indicator that there's big hail that radar beam is bouncing off of. So anytime you see a three-body scatter spike like that, you're probably going to see a severe thunderstorm warning with it. The only instance where maybe that's not going to happen probably is if it's just a really deep warm layer and the hail is just not going to be big enough by the time it gets to the ground. But in most cases, that's going to probably be enough to prompt to a severe thunderstorm warning. So let's continue on here. Another indicator of a very strong updraft and potential for hail is something we call a bounded weak echo region. And what we're looking at here is a supercell. This is actually from that March 2nd, 2012 Henryville tornado. So this is your classic supercell. You've all seen and probably heard or seen on TV the hook echo that we talk about. That's what you're seeing right here. And you see the purples and the whites. That's a very heavy precipitation core with big hail in it. So one feature that we look at, and well, before we talk about the bounded weak echo region, I did want to talk about why does a supercell hook? Why do you get that hook feature? And it goes back to our updraft. So your updraft is actually, here in this kind of clear area where there's not precipitation. And again, because that's all warm, moist air rising, but then your precipitation falls out, downwind of your tilted updraft. Okay, so what happens is since that updraft is rotating because of vertical wind shear, and again, we're going to get into a lot of that, it rotates counterclockwise. So it pulls that precipitation around the backside of the updraft. And so that's why you get a hook echo. So I just kind of wanted to show you that. So again, your updraft is kind of in that clear area just ahead of where it hooks around. All right, so what you get with a strong updraft then in a supercell is, initially there's no rain in that updraft area, but the higher you get aloft, you actually start to get an overhang of that precipitation core as that updraft tilts. And so, we've gone up a little bit in our elevation here. Now we're looking at 2.4 degrees, which is about 9 or 10,000 in this instance across the above the ground. And so that's like the mid levels of the storm there, low to mid levels. And then if you go higher up, look at this. And again, what you're seeing here is you're seeing the really strong reflectivities in a full circle around the weaker and lower reflectivities. And that's what we call that bounded weak echo region. And really what you're seeing here in the middle, this little donut hole here, is actually the updraft. And again, that updraft isn't supposed to have any or very much precipitation in it, but it's so strong that it's actually punching up through the core of the storm, and all the precipitation's falling out around it. And so here we're looking well into the mid levels, 14,500 feet. So anytime you see a bounded weak echo region on radar, and again, you have to look aloft. You're probably not going to see that on the lowest scan, but you have to look at higher up in the storm. If you see that, you have a very strong updraft and a good potential for hail and severe winds. So we call it a BWER, or a bounded weak echo region. And then going up, 29, 30,000 feet, so you're well above, your freezing level here. And if your core aloft is still very strong up that high, very good chance you have severe hail. And then one thing that makes it even more likely that you have severe hail is if that storm is rotating, because not only do those hailstones bounce around with a strong updraft, they also stay up there longer because that updraft is rotating, and it keeps those hailstones cycling around. So a rotating supercell has high potential to produce severe hail anyway, but it has a chance to get giant because it also rotates and keeps the hailstone up there longer to get bigger. So those are the things we look for. And again, that's just another way to look at a storm through a kind of a vertical depth. Again, what we see on the radar screen a lot of times is just one flat image of a storm, But really, to get the full idea of what's going on, you kind of got to look at a cross section or almost a 3D view of it to really understand. And again, that B word is right here in this little weak echo area. And again, that's indicative of a very strong updraft. So, and here's some examples of some giant hail that we've had in our area. On that left, that's at least some tennis ball to maybe even some baseball sized hail. And on the right, Carroll County, I mean, that's either softball or grapefruit sized hail probably. So giant hail. And again, we got that out of some of those supercells that occurred on that day. Okay, so we've talked a lot about how storms form, instability, why that updraft rises, and some things that can limit it like caps and things like that. So now let's get into, once that storm develops, what causes the type of storm that you see? And just like a lot of things, there's a kind of a wide spectrum of types of storms, from your single cell, we call these like your garden variety or pop-up popcorn thunderstorms that you see on a warm summer day, to that generally have the least threat, to your big squall lines or multi-cell clusters that are driven by a large cold front, to your big daddy, which is the supercell. And again, it's the wind shear that actually drives what type of storm mode you're going to see. Okay, so let's go through this in detail, because this is pretty cool. All right, so we're kind of back to some of the basics here when we talk about an updraft, right? So if you look at this little cloud on the left, this developing thunderstorm, and when we talked about the thunderstorm life cycle or the stages, we talked about that developing stage into the mature stage. In a situation where you have very weak vertical wind shear, so what I'm talking about vertical wind shear, I'm talking about increasing winds with height. If it's very weak, like in the summertime, a lot of times that updraft is just going to go straight up. It's going to start to produce precipitation once it gets to a certain point, and then that rain-cooled air is going to fall right back down on that updraft and choke it off, cool it off. So that storm will go up in 10-15 minutes, and then it'll collapse just as quickly. And generally, you won't get a severe thunderstorm out of that. You may get a gust of wind as it collapses, or you may get some briefly small hail or marginally big hail or whatever, penny size, nickel size, maybe a quarter size hail. But for the most part, these are pretty harmless storms. Your bigger threat is a brief period of heavy rain and lightning. But again, what you need for a thunderstorm to survive much longer and become more organized is you need increasing wind speed with height. And so that's what we talk about, this wind shear. And what that will do is that will tilt that updraft, not completely topple it over, but it'll tilt it enough that once it starts to precipitate, it actually falls away from your main updraft, and your main updraft is able to survive and continue going. Now, there's another component to this wind shear that we'll have to talk about. Not only can you get increasing wind speeds with height, but if you get increasing wind speeds with height and turning winds with height, you can create that rotating updraft or that supercell. And once you get a good supercell going and a good updraft established, it can create almost its own environment, and it can survive for hours. A lot of times, if it's just a multi-cell type of a storm, you get more sustained life, but overall, it's not going to last for hours and hours and hours. With a supercell, and that's why we ended up getting one of the longest tracks tornadoes with that December 10th, 11th. And I mean, those supercells tracked for several hours from northeast Arkansas across northwest Tennessee into western Kentucky and then into central Kentucky before they dissipated. And it takes a very special type of an environmental setup to do that, and that's all driven by wind shear. Okay, so again, I just wanted to provide you some tools if this is interesting you, and you can kind of again follow along and apply some of this, what you learned this evening to even tomorrow's event. So if you go back to that Storm Prediction Center page and go to that meso analysis, right next to where you clicked on the thermodynamics for the CAPE, you can look under wind shear. And generally you want to look at like your 0 to 6 kilometer shear and just some quick values that you want to look for. Anything less than 25 knots is generally going to be too weak to sustain an updraft. So in that environment, you're probably just going to get cells that quickly develop and then die off, your pulse storms like we talked about in the summer. Anything 25 to 30 knots is kind of marginal for organization, but you can start to get, a little bit better severe threat with, anything in that range. And then, 30, 40, 50 knots, that's when you're really getting into a very sheared environment, and your chances for severe weather go up if you have instability as well. So again, just kind of, if you're unsure about a parameter, as you click on that wind shear, there's a little question mark next to it. And again, it may be kind of meteorologically heavy, but if you're really interested in it and you just kind of follow along, you can really pick up on things and learn pretty quickly about some of this stuff. So okay, let's talk about that storm spectrum again, and let's start off with our kind of most common and simple storms. And so these are our single cell or general thunderstorms, kind of our popcorn, midsummer type storms. And again, the biggest threat with these is going to be lightning, brief heavy rain, and maybe some gusty winds, or brief, small hail. But this little slide I created here, and y'all can laugh at this if you want. It took me like an hour to create this. But I kind of wanted to give you an idea of what type of environment these single cell or these pulse popcorn type thunderstorms develop in. And again, to kind of place yourself in the middle of summer, say it's like a hot July day, and you wake up in the morning and there's no real clouds in the sky, but by early afternoon, mid-afternoon, you start to see some pretty aggressive cumulus clouds that are starting to develop and heat up with the day or whatever. A lot of times you're not going to get just thunderstorms alone in that environment. Number one, if you imagine this kind of weather pattern that I've drawn crudely on this map, if you think about a high pressure, a lot of times you get that kind of over your area in the summer. And a lot of times high pressure is associated with sinking air. So and a lot of times right where you're close to the high pressure, you're going to have a big strong cap that you're not going to break. But we get in these environments where you kind of get on the edge of the high pressure and kind of still close to where the jet stream is traveling. And we call this a ring of fire conceptual model. So that's actually stolen from a geologic term when you talk about the tectonic plates in the ring of volcanoes that extend around the Pacific Rim, like this little graphic I've shown up here on the upper left. And so what happens is if you get on the edge or the kind of the periphery of these upper ridges where there may be still a little cap, but it's not very strong, you can still get little disturbances. And this is where I crack myself up because I made this little animation where this disturbance comes through the jet stream, and it can be just enough to trigger thunderstorms. Remember, we talked about lift and triggering. Sometimes in the summer, you're still pretty unstable, and it doesn't take much to break just a little cap and trigger thunderstorms. And so we get storms that will pop up in this ring of fire conceptual model that we talk about. And again, it's not usually a very high severe threat with these. Maybe you'll get a few marginally severe storms, but most of the time these storms develop and then die off very quickly because there's very weak wind shear aloft, and that's because the jet stream is usually displaced a little bit too far to the north. So here's an example of popcorn variety type thunderstorms. And again, you'll watch any individual core that pops up, and they'll briefly look pretty strong, but then they usually kind of develop or collapse or weaken pretty quickly. And so that's kind of an example. And what that looks like on velocity, before I get to the velocity, I want to show you this. So what you can get out of these when they do collapse is you can get a microburst. A lot of times, again, the storm's too weak, but if it does get strong enough, it can actually, that collapsing storm, because if you think about it, the updraft goes up, it's a very strong upward vertical motion, warm, moist air. But then when that updraft comes down, that's a whole bunch of rain cooled air. And it gets a lot of downward momentum as it comes towards the ground. And if you think about a garden hose hitting like a concrete pad or something, when that water hits the ground, it spreads out rapidly. And that's exactly what's happening with a microburst. Another good analogy is if you've ever been to like a Great Wolf Lodge or something, one of those indoor water parks where you have those big play things, water features that has like a giant bucket, and every 5 minutes or so that giant bucket fills up with water. And then when that spills out, if you've ever been standing near that, you get a big gust of wind when that water comes crashing down. And it's the same concept. I mean, you get a whole bunch of rain cooled air. It gets really a lot of downward momentum. And it can produce a microburst as these storms collapse. And one thing you'll look for visually as a spotter is a rainfoot, which is basically that cold, moist air spreading out against the ground. I was actually able to take GR analyst for this storm in Shelby County way back when. This produced 70 to 75 mile an hour straight line microburst winds. And you can see that microburst actually filtered out of the velocity in that storm. So I thought that was pretty cool, and is a really great example from a radar perspective of seeing a microburst in real time. So that is one hazard to watch for with these simple storms. Got a video, it should play here. Microburst. Huh, it's not playing. That's weird, it worked earlier. No, it's not playing. It's an old video. And again, basically just shows that blob of rain coming down to the ground and then spreading out as it hits. If you've seen the basic spotter training, you've seen this video, I'm sure. So we'll move on. And again, here's just another example of a core aloft collapsing. And again, that's what can create, your hail at the surface or a microburst as all that downward momentum comes to the ground. So here's what a microburst looks like on velocity. And this is actually right near Louisville International Airport. You can actually see the radar's down here at the bottom of your screen. There's this little dark circle. The green is velocities towards the radar at about 30 knots or so, 25, 30 knots. And the red is velocities away from the radar. So you can see that hitting the ground and spreading out. But if you think about, 30 knots each way toward and away from the radar, the source of that was probably 50 or 60 knots. So they actually had a severe wind gust at the airport with that microburst. That's what it looks like, and that's what we're looking at on radar when we're trying to issue warnings for these types of storms. Another thing you get with collapsing storms, especially in the summertime, mainly because there's a lot of dust and insects that these outflow boundaries can pick up. But what you'll see is these little lines spreading out from collapsing thunderstorms. And really what it is that's that rain-cooled air that is spreading out from the thunderstorm. And it's really, you can think of it like a little mini cold front. And you can get a really good gust of wind from an outflow boundary that's even extending, 10, 20 miles out away from a storm. Because again, it's all that momentum. It's much like the anvil spreading out across the top of the atmosphere. When all that downward momentum from a downdraft hits the ground, it spreads out across the surface. So again, watch for gusty winds with outflow boundaries. You also have to watch for outflow boundaries colliding with other outflow boundaries. That can create, if you watch right here, boom, there's an explosive thunderstorm that develops where those two boundaries collided. That basically, if you think about it, there's a lot of energy and momentum colliding, and that air parcel has nowhere to go but up when these collide, and it triggers a new thunderstorm in an unstable environment. So pretty cool kind of to see how that evolves. But yeah, definitely watch for outflow boundaries because you can get a thunderstorm pretty quick. And really, again, what you're seeing on radar is you're actually seeing dust and insects being picked up by those gusty winds at the surface. So one thing you won't see is if you are far away from a radar, you won't see an outflow boundary because it'll probably overshoot it. The radar beam rises with height. Okay, so moving on. And again, I'm going to kind of go through this fairly quickly. We see a lot of squall lines, and the biggest threat with those is damaging winds, pockets of damaging wind, as well as heavy rain, but we also get spin up tornadoes within these squall lines. So again, this is where you're going to see your shelf cloud on the leading edge, and it's going to cover 200-300 miles. Again, it's usually a cold front that's driving something like this. And again, your main threat's damaging winds, heavy rain, lightning, flooding, but you can get spin up tornadoes within these squall lines. So here's an example from the February 5th, 6th, 2008. We called it the Super Tuesday event. I think there was actually like an election going on that day, a primary election. Here's just another example, and don't really look at the circles. Those are just our airports that we issue forecasts for, but wanted to show you from a velocity and reflectivity, standpoint, what a kind of a squall line looks like. And there's instances here where you can see the storm is kind of bowing out, which that's indicative of pretty strong wind gusts. So again, your main threat is wind, but we'll show you several examples of spin up tornadoes within. Here's just another example of a squall line approaching. Again, you're going to see a shelf cloud right on the leading edge of that. So you're going to get the wind and rain immediately once that shelf cloud gets over you. Okay, so what we have to watch for, and these are very tough from a warning operation standpoint, because they usually spin up very quickly and then go away very quickly. They're also shallower with respect to rotation. Yeah, they can produce quick spin up tornadoes. They also aren't as obvious as something like you'd see with a supercell in the reflectivity. Sometimes you'll see a little hook, but you really need to pay attention to your velocity on these types of storms. So here is an example where it's really close to the radar. And again, red is motion away from the radar and green is toward the radar. So what you're seeing here is a tight counterclockwise rotation. and it's associated with this little hook or little nub that we see on this squall line. And yeah, that produced a little tornado. So again, pretty short-lived. Usually EF0, EF1 type damage, but you can get stronger, you know, with a strong system. Here's another example. And again, you almost have to, you would never know it by just looking at the reflectivity with this type of a storm. But look at the velocity here. You can see it pretty clearly. There's a nice tight rotational couplet. And again, you wouldn't, no, there's no real clear evidence in the reflectivity like you would see on like a supercell. And I'm just going to kind of show you several examples here. They can be really subtle. You know, from a velocity standpoint, this rotational couplet isn't that strong, but again, it doesn't take much in some of these environments where you have just a little bit of instability and a ton of wind shear to produce and get that wind damage down to the surface. So just another thing we look for here. And here's one more. Again, just kind of a subtle little rotational feature right here. Here was an event we had back a couple days before the December 10th and 11th event, and this was a squall line, a quasi-linear convective system, what we call it. And sometimes we look for these line break signatures, and you can see the line break and the reflectivity happen right here. And we actually had two brief tornadoes touch down. One was near Frankfurt, and one was in Scott County, closer to Georgetown. So again, most of the time they're weak. There would be no reason to even try to chase storms like this. A lot of times they're moving very fast. Two, they're going to be wrapped in rain, so you're never going to see it anyway. And you know, us being in Kentucky here, we have a lot of terrain, a lot of trees. I would never try to chase a squall line. Again, you're not going to see anything anyway. And all you're going to get is maybe potentially put yourself in a dangerous situation because you would never see a tornado coming. And plus they're so fast moving that, you know, with the curvy, hilly road system around here, you'd never be able to keep up with the storm anyway. So it'd be best just to maybe spot the shelf cloud on the leading edge of any one of these and then report what you get. And of course, report any damage that you see. So yeah, but you can get, you know, within a squall line, you can get several tornadoes, again, most of the time weak, but if you get an embedded supercell within a squall line, then you can get, you know, pretty much tornadoes as strong as what you'd see with a regular supercell. One of the best examples of a squall line or a supercell embedded in a squall line was back in September 20th, 2002. Up through central Indiana, there was a very long track supercell that moved up a squall line, and it produced EF2, EF3 damage south side of Indianapolis up through the northeast side, and then parts, you know, well south of Indy and even to the northeast of Indianapolis. So I was in college at the time, so that was kind of an eye-opening type of an event from my perspective. But yeah, that's probably the best case that I can remember. Like we said, spotting squall lines is dangerous. I wouldn't even try it, especially around here. Again, storm motion is usually too fast, and you're not going to see you know, anything anyway, because it's most of the time going to be wrapped in rain. The duration is also very short-lived. And another limiting factor is a lot of times these happen at night, so you're not going to see anything anyway when that sits. So we're going to kind of go through this quickly and kind of use this as an example too. You know, we sit here and we preach about storm chasing and spotting storms, and you got to do it safely. And again, this isn't the best area in the country to do it safely because of the terrain and the trees. You know, out in the Great Plains, you can see a lot better, and you can, you know, more safely keep your distance. But this is, you know, just wanted to remind everybody that even the most experienced chasers, you know, tragedy can happen. This was Tim Samaris's vehicle after the El Reno tornado. He was a very well-respected chaser, actually a self-taught meteorologist. He was an engineer in the military, and he was the one that put probes in front of tornadoes and had quite a bit of success with that. But anyway, got in the wrong place with respect to the El Reno tornado, and him and his son and another person got killed. So again, we're not really necessarily promoting storm chasing when we do these types of talks. What we're promoting is just learning about weather and learning about reporting severe weather. And if you are in a position where you can safely spot a storm, then that is okay, but we really don't promote chasing storms, especially in an area of the country like this. So I did want to get that in there. One thing that we talk about with respect to, you know, damaging winds and these brief spin up tornadoes and squall lines is when we're out surveying these, a lot of times it's hard to tell the difference between straight line winds and brief spin up tornadoes. And the reality is that you can get just as strong of straight line winds as well as a weak tornado. So you can easily get 90 to 100 mile an hour straight line winds, which is equivalent to a solid EF1 tornado. So I would ask you, can you tell the difference between which one is tornadic in this instance versus straight line winds? And so a lot of times people say, well, it just had to be a tornado. That's not always the case. And when we're out surveying, there's several things that we look for. We actually use drones here at our office now too, which gives us more of an aerial perspective. That's very helpful. But just because you heard a roaring sound with respect to wind, all strong wind is going to roar. So that doesn't necessarily mean it was a tornado. Debris stuck in the ground. I hear that a lot, that it had to be a tornado because the debris stuck in the ground. That's not really true. I mean, if you get a building that flies apart as it flies through the air, and you've got 2x4s flying everywhere, those are gonna stick in the ground when that structure hits the ground again. That doesn't necessarily mean it was a tornado. Sometimes you can use that evidence to determine it was a tornado if it perhaps gets thrown back upstream, because that would tell you then that the debris was rotating around a funnel. But a lot of times if it's thrown downwind, especially in a divergent pattern, that it very well could have been straight line winds. So those are just a couple examples. We do look for mud spatter on the backside of a house, that's basically upwind of where the storm was moving from. That would give you an indication of rotation. Convergent pattern in the debris, if trees are all laying in the same direction, then a lot of times that's not indicative of the tornadic activity. But if everything is laying in several different directions, especially in a convergent pattern, then that does give you a pretty good idea that you did have something tornadic. And again, we'll match it up with the radar. So if the radar supports tornado or the atmosphere supports tornado, and the damage looks like it could have been tornadic, then a lot of times then that will be the conclusion. But bottom line is, as a spotter, you don't really need to be the one to kind of tell us what you think happened. More just report the damage to us and then let us take a look at it. So let's get to the last one, the supercells. I'm trying to go through this here pretty quickly. I know we got about 5 minutes left. We're going to go a little bit over, but again, I want to get through this. So supercells, again, very complex. They're not just a straight updraft and downdraft. Again, what you get is you get that tilting updraft, and then you get that rotating updraft, because wind shear increases with height, and then it also turns with height, and it creates a counterclockwise rotating updraft column. And so, you can see several of the features that we talked about here. Here's your tilted updraft with your anvil and your overshooting top. We now know why that occurs, because we can understand soundings and instability a little bit better. You also get a downdraft where the precipitation core really starts to rain out, and that actually creates a gust front on the leading edge or the forward flank of the storm. And then you also get those mid-level winds actually wrap around the updraft and then come back down on the backside of the storm as a rear flank downdraft. And where that updraft and the inflow into the storm interacts with the rear flank downdraft, that's where your tornado is going to be. And really, the more recent research and study about tornado genesis, really, it appears that the rear flank downdraft plays a pretty important role. It's not just the updraft that stretches, that horizontally rotating wind into the vertical, but the rear flank downdraft also plays a role. So knowing how complex a supercell is very important, and knowing where you're at with respect to spotting a supercell is critical. And again, this is going to be the easier type of storm to spot a lot of times, but it's also a more dangerous type of storm. So you have to be very mindful of where you're at. So here's what it looks like on reflectivity. And again, we talk about that hook echo. And again, that's because basically that precipitation is wrapping around counterclockwise rotating updraft. Almost all supercells are right moving counterclockwise rotating. I did want to mention you can get a left moving supercell, which rotates actually clockwise. But those are more just most of the time hail producers. Very rarely will we ever get a tornado out of those. So back to the right moving, more common supercell. So again, here's what it looks like, and now here's what the kind of different features of that updraft of that supercell look like. Your updraft is again in that kind of clear area, and again it rotates counterclockwise. So all that precipitation wraps around the backside of the updraft, and then you've got your rear flank downdraft that wraps in. And kind of right where that updraft and rear flank downdraft meet up is where you can get your tornado. Okay, so we're going to look at what that looks like from radar and visually. So rising airs, again, it's often rotating. It's at the heart of the supercell. And it's fed by inflow and the warm, moist air from the right of the storm's path. So again, it's that clear area out ahead of that hook. That's where your updraft is, okay? So there's your updraft, like we just described. Now, the main precipitation core, that's another part. You don't really want to be anywhere near this because all that's going to be is hail and heavy rain and a lot of lightning, and you're not going to see anything if you're there, okay? So that's the forward flank. That's where, you know, again, heavy rain, downburst winds, lightning, hail, all that's going to be there. Stay away from there, and all that kind of expands outward, just like we talked about with a collapsing thunderstorm. And then the rear flank downdraft, again, more recent research has shown that plays a pretty critical role in tornado development. So you can get a really strong wind gust on the backside of a supercell because of the rear flank downdraft. So, but in general, you know, it's, if you're going to be anywhere, that's going to be better than being, you know, right in the direct path, you know, ahead of the supercell in the warm sector. If you are gonna, well, we'll get to where to spot them here in a second. So let's move forward here. So where the RFD interacts with the updraft, that's where your rotation, your development tornadoes is most likely. So right here, and you can actually see there in this radar image, there's a little debris ball. So those little purples, that's not hail in that instance, it's actually debris being picked up by that storm. So let's look at what this looks like visually. So here's just a classic look. Again, your updraft base, your wall cloud, here you're seeing and the actual tornado coming out of the wall cloud. But again, so your warm moist air is going to kind of be coming from the right, the lower right of the picture up into that updraft. Your downdraft, your rear flank downdraft is going to be coming kind of through this clear area back here around the backside of the tornado, kind of where I have that yellow dashed line in the horseshoe. And again, where that updraft and downdraft meet, that's where your tornado forms. And so, like I said, a lot of times you'll see a clear slot in that instance. Here's a really good shot of it. So you see that clear slot where the light is coming through. That's the rear flank downdraft, and then you can see a really well-developed wall cloud where the warm moist updraft is. And again, right where those two kind of interact with each other, that's where you can get your tornado. So again, the best place to view that is to the south, kind of to the south basically of the warm sector. All right, you don't want to be up in the warm sector right ahead of where that hook echo is, because that puts you right in the path. So you want to be south, but you should still be able to see pretty clearly into that updraft region. You know, if you're not too far south and there's not too much obscuring your view. So really the best advice about spotting a supercell is to get to a place where you have a pretty good vantage point that, you know, you think that the supercell will pass, you know, fairly close to, but just to the north of, and then sit there and wait and you know, and watch that storm pass. Again, don't really condone chasing any type of storm, especially in this type of area, but you know, the supercell does provide a little bit better opportunity to do that as long as you can leave yourself a southward escape route. So, and you always want to know which way the storm is moving. Here's an example of what you might see kind of standing in the southern part of, whoops, hold on, sorry, I got ahead of myself here. Inflow. So this was the Henryville EF4 tornado, and hopefully bandwidth is allowing you to see this video, but you don't really want to be this close with debris raining down around you. The person that took this video had quite a bit of guts, but in general, and if you look at this tornado, this was a violent EF4. You can see the multiple vortices here when it comes out on the other side of this tree here. Yeah, that was a nasty tornado. So this next video is kind of really more where it would be a safe vantage point. So this person parked on an overpass where they could see very far, and you know, let the supercell pass by to their north. And you know, again, they had a very clear and unobstructed view of the updraft. So just again, a very impressive tornado. That tornado was moving at 60 miles an hour. It covered 40 miles in 40 minutes. So it was moving right at 60 miles an hour. And again, you can see the multiple vortices here. This was when it was going through the Clark State Forest. So again, just wrapping up here real quick, the usual principles apply. Know your position with respect to the storm and the storm's motion. So again, this looks like it's a safe place and everything as long as that storm is moving to the north and east, which in this case it is, okay? But if it's moving from northwest to southeast, then does that look like a good position to be in? Absolutely not, because then it would be heading right for you. So again, you really want to know which way that storm is moving, and you can kind of judge based on inflow into the storm, and so say you get in like a good south breeze at your back heading right into the storm, then you're still in the inflow section. If you suddenly get a really strong kind of a west wind as the storm is passing by, then that's probably the rear flank downdraft taking over at that point. So you're kind of past the inflow section, and you're going to be safe in that area except for maybe gusty winds, but where you don't want to be is right in the direct path in the warm sector basically. So those are good rules of thumb to kind of to spot by. Again, it's very important to know where you're at with respect to that storm, and again that's really not just supercell, that's really with any thunderstorm. Kind of learn more about wind patterns and wind flows. Hopefully you've learned about them with respect to each type of storm mode as we've gone through this. So I think we've kind of hit that enough. Again, don't be in the precipitation core, the forward flank downdraft where that red X is. You can be back behind the storm, but you're probably not going to see as much because of the rear flank downdraft. And you don't want to be right in the storm's path. You want to be to the south of it. And there's just another great example of that rear flank downdraft punching in. You can see the kind of the horseshoe in that clear slot cutting in south of the tornado. And again, your warm, moist inflow into that updraft is going to be coming from the lower right part of the picture up into the updraft there. So a really good shot there. And again, just remember that storms don't always move from southwest to northeast or from west to east. You can sometimes get a supercell in a northwest flow, late summer type of a pattern. So again, you just have to apply which way that storm is moving with respect to where you're at. Okay, so that was all I had. So now I just kind of want to briefly tie everything together for 5 more minutes here, and then we'll be done. We can ask some questions. So here's tomorrow's outlook. And again, you can see that level 3 enhanced is over all of Western Kentucky and even almost into Central Kentucky, basically west of the I-65 corridor, and even some pockets of level 4 moderate risk over, kind of the Ozarks region and up into the Quad Cities area of, Northwest Illinois, Eastern Iowa. So let's take a look at our probabilities real quick, since we kind of covered this. Your hail probabilities. In general, we're not really expecting much of a hail threat in our area in Central Kentucky. Maybe you could get some marginally severe hail. That's not really what this type of system is. This is going to be more of a wind and potentially, a few spin up tornadoes type of an environment. So you can see a 30% probability of a damaging wind event within 25 miles of a point west of I-65. It's only 15% as you get east of I-65. And then same with the tornado probabilities, 5%, west of I-65 and even 2% into Eastern Kentucky there. And again, that's within 25 miles of a point. So that's across a region. So why is it that, this threat of severe weather is going to diminish the further east those storms get? Let's take a look at that. Okay. So, and again, this is putting it all together. We talked about CAPE and we talked about shear, and those are 2 very important parameters with maintaining storm strength. So this is actual model data that I gathered from this afternoon for the storm system tomorrow. And so what I did was I took a snapshot of our expected instability or our CAPE at 5 p.m. tomorrow afternoon, evening. And you can see on this color scale here that out to the west over, basically along the Mississippi River Valley in general, there's some values that are over 1,000 joules of instability, even up to maybe 1,500. And again, that's not a lot in the summertime, but in a cool season when we have a ton of wind shear, that's a lot of instability. Now watch what's going to happen. If you look further east, as you get into Western Kentucky, the values decrease a little bit. And then as you get over us, initially, we aren't going to have any instability over us. But as we go deeper into the evening, we get a little bit, the overall instability weakens because you lose the heating from the sun. But you still have it moving eastward. So 8 p.m., there's still plenty there, especially across Western Kentucky and the Missouri Boot Heel, Southern Illinois. And then as we go to 11 p.m., it is moving into our area, but it's weakening. So if you remember that outlook, it shows, kind of lesser threats the further east you get. And you can kind of see that in our available instability, as we go from 11 p.m. to 2 a.m. over our area. There's still a little bit. There's maybe 100 to 250 joules of CAPE. And again, that may be just enough to get some damaging winds down to the surface, or maybe a few brief spin-ups tornadoes, but it's not going to be probably that widespread. Their better threat is over western Kentucky and the Missouri boot heel in those areas, because there is more instability earlier in the evening as those storms approach. So we talked about the shear. So, and remember, we use the kind of 30 knots as a good threshold. Well, look at our shear. We have 50 knots over, a good chunk of the whole eastern part of the country. So shear is not a problem. And in these cool season events, it really never is. There's always going to be plenty of shear. So what I did was I looked at the significant tornado parameter, which is a combination of your shear and your instability. And again, you're going to see that same trend where the values are pretty high out to the west, where those high category outlooks are, the level 3 and level 4. And then as we go through time, so this is 8 p.m. As we go through time and that moves east, there's 11 p.m. it weakens, and then 2 a.m. it weakens even more. Now there's still some, instability and plenty of shear, so we can't rule out a few, damaging winds events and spin up tornadoes. But it basically weakens the further east you get. So that shows you exactly why that outlook is kind of positioned the way it is, with the threats diminishing the further east you get. And again, I just kind of wanted to apply that instability and shear to tomorrow's case to kind of show you, what that looks like. So then one more thing, let's look at those soundings that we just looked at. So here's a sounding across southern Illinois further west where you're in a category 3. And remember, where that dashed line is to the right or warmer than the environmental temperature, that's where you have instability. So you can see the instability through the mid levels, and it actually equates to about 1,000 joules of CAPE, which again, for the cool season, that's pretty good. There is a little bit of a cap, but that's very weak, and that will likely be overcome by the cold front and any very strong forcing from the system. Also look at this wind shear profile. So very, very strong winds just off the surface, going up to 55 to 70 to 80 knots, and they're turning with height. You see that as you go up in height? So that gives you that rotating storm potential. And if you look at this up here, we call this a hodograph. So that tells you how much turning is in the storm. So again, out west, yeah, definitely a tornado potential and damaging wind potential, looking at that sounding. Now, let's move just a little bit further east into, say, kind of around Jasper area, southwest Indiana. Notice there's less instability. Now we're down to like 500, 600 units, and there's more of a cap there. So there's a little bit stronger inversion that's going to limit some of that thunderstorm growth. But, again, you might still be able to erode that, just as that line of storm gets there because of the cold front and the forcing. And again, there's that really strong wind speed with height, and it's also turning. So again, if you get something going, you can definitely get a tornado or a damaging wind event in that environment. Now let's move one more place to the east over towards Lexington. So again, this is where we expected less instability. Look at those soundings. Now you don't have anywhere where that basically that air parcel is warmer than the environmental temperature. So, and look over at your values, there's basically no CAPE, 4 joules, which, is pretty much non-existent. So that matches up with that outlook, expecting there to be less of a threat the further east you get. So again, that's just kind of tying everything together, showing you how instability can help drive a forecast, and also how wind shear can, affect your storm mode. So I hope you found that useful. And again, follow along tomorrow with some of the tools we've given you, and kind of try it out in real time and see if you can notice some of the things we talked about today. So with that, I will take questions. I'm sorry I ran over. I know that was a ton of material, but I figure since we haven't done this in 10 years, if we go 15 minutes over, that's not so bad. Again, look for that link tomorrow to to just fill out a quick form to get your advanced spotter certificate. And I will try to go through here the questions. Let's type your questions in that questions box if you can, and I'll try to go through those and answer as many as I can. Hang around for a little while here. So appreciate everybody taking the time to watch this, and yeah, we'll try to do this more often since we've had such a good turnout. I think I had pretty much between 210 and 220 people on the whole time. So Also, thanks for staying on. Hope you all enjoyed it. So let me see if I can answer some questions that may come in here as we go through this. Okay, here's a question. If an updraft goes up, then how does it become the same temp as its surroundings? If the higher you go, the colder it gets. Okay, so what's happening there? It is actually when the air parcel is rising and cooling, it is not cooling at the same rate that the air is cooling with height. So in other words, it will cool slower than the air is cooling with height, especially in the mid levels where you can get some really sharp temperature drop offs with height. Again, we call those mid-level lapse rates. So again, it's going to cool with height, but it will cool slower than the air does with that same height. And so it will continue to remain warmer than its surroundings, and it will continue to rise and be buoyant because of that. So that's a good question. So hopefully that makes sense and answers your question there. Let me scroll down here. It says, will it be available to download? I think this is going to be recorded, so we will make it available. We'll either put it on our YouTube channel or yeah, that's probably the best way. Look for it, and we'll share a link to that. If you follow us on Twitter or Facebook or whatever, we'll share a link to it. That way you can access it on a YouTube channel anytime you want. That's probably the best place to put it. Because even though this data that we looked at for tomorrow's event, it kind of dates this a little bit, it's still a good case where you can actually apply what you learned to a real-time scenario. So I think that will still be just fine. So good question there. So yeah, we'll let everybody know when we make it available, hopefully sooner than later. Let's see here if I have any other questions. Okay, here's a question. Why doesn't it thunder when we have bad snow days? Okay, so you all have probably heard of the term thunder snow, and occasionally you can get enough instability in the atmosphere to create a little bit of thunder when you get a heavy snow. The reality though is the systems that create big snowstorms a lot of time are more what we call stable systems, and there's really not true instability in the atmosphere. Now there is rising motion because of cold fronts and things like that, and the upper level jet stream and upper divergence that basically creates a very deep column of rising air. And of course you have plenty of moisture to go along with it, but there's not true instability where you have the beach ball rising up from the pool, 50 to 100 mile an hour updrafts. It's actually more like the air rises at like centimeters per minute type of a rate, so much slower, more gradual lift. And so every once in a while you can get a strong enough system to have just enough instability to get a little bit of thunder, but in reality those are much more stable type systems. And so even though I say stable, that doesn't mean that you still can't get upward vertical motion. It's just not very intense upward vertical motion like you get with instability and full-blown updrafts. So that's a good question. I hope that makes sense. Another situation where you can get thunder is with like snow squalls. And believe it or not, that is actually a very similar process to thunderstorms. It's actually a convective process. It's just through a shallower depth of the atmosphere. It's not 40, 50, 60,000 feet. It's like 10 to 20,000 feet. And so usually you need a little bit more depth to create lightning. But with snow squalls, you can actually get enough depth for lightning. So really good question there. Okay. Yeah, I'm sorry about the screen not being in the right mode the first half. But I'm glad we got that fixed. Thanks for all the suggestions there. Okay, so in a car and a tornado hits, where is the safe place to go? All right, so the best advice I can give to you for that is don't be in a car in a tornado. And I know that sounds, that's not very helpful, but really the best thing you can do is be situationally aware and try not to allow yourself to be in that situation to begin with. Because let's be honest, if you get hit by a tornado and you're in a car, there's a good likelihood you're going to get injured or killed. So here's the options. If there is a tornado bearing down on you and you cannot get out of its path, then what I would do is try to find a safe structure, whether it be a building. And I don't even care if you drive up to a house that you don't know the person, bang on their door and say, please let me in, that type of thing. Again, you're pretty much going to be riding it out if you're in a car, and you're going to have to hope for the best. And, people sometimes say, get out of the car and lie in a ditch. And I don't really know that that's what I would do in that situation, because let's face it, unless that's a very deep ditch, you're still going to be exposed to debris that's being picked up by that tornado and being thrown out around everywhere. There's a good chance you could just get flat out picked up by the tornado and sucked up. You also have to worry about if you get hit in the head by a piece of debris, but aren't killed, but then there's a ton of heavy rain with that storm. What's the first place that's going to flood? That ditch. So if you get knocked unconscious, there's a chance you could drown in that ditch. So yeah, I mean, quite honestly, I think I would take my chances in the car. But yeah, the best solution is just try not to get in that situation and be more aware of your surroundings to begin with. Back in the 90s, early 90s, there was that video of the news crew that went under the overpass on the Kansas Turnpike, outrunning a tornado. They couldn't really outrun it, so they hit under the overpass. And that was at the time viewed as a success story, but in reality, later on, the Moore, Oklahoma tornado, May 3rd, 99, somewhere in that time frame, was an F5 tornado. People hit under an overpass and they got sucked out, because really what happens is the winds get funneled underneath that overpass, and it actually strengthens the winds. It's the Bernoulli principle, I believe. So if I had nowhere else to go, I would maybe give it a try, but that's not something you want to do, is just suddenly, if during a storm, pull over and try to get up under an overpass. Another thing that happens on interstates a lot of times is people will try to, just pull over under overpasses. And if it's raining really heavy, traffic that's still driving along doesn't see it, and suddenly there's a whole bunch of stopped cars, you can cause a pile up in that scenario. So that's happened a couple times. So in general, again, situational awareness is really your best tool with respect to vehicles and severe weather. And again, even though it's not recommended to try to outrun a tornado, quite honestly, if I have a path that I can get out of that tornado by driving, that is going to be my first option. Okay, so let's see here. Other questions. Moving on. That is a good question. Is there an updated same county codes list for Kentucky? I tell you what, if you Google that, I'm sure that you could find that. Just pretty much type in same county codes, Kentucky, and I'm pretty sure that would bring you to a list of those codes. I assume you want to program a weather radio. So yeah, that's where you would want to go for that. Yeah, we are going to record it and put it on YouTube. So good question there. Moving on. Are there any other apps other than MPing to place reports that I can get directly to the NWS? As far as apps go, I know that's probably the best one. That it would pretty much, it pops up into our workstations actually almost immediately from MPing. Other options would be, if you join CocoRaHS, you can submit rainfall reports as well as hail and snow reports. CocoRaHS. If you Google that, that should direct you to ways to sign up for CocoRaHS. So that is kind of a way to get us reports. But quite honestly, other than MPing, the best thing is to just call us or email us or social media. Get a hold of us that way. So that's a good question as well. Sometimes the MPing reports to like for instance, like wind speeds, it's very vague. It'll say something like broken branches to snapped trees. and it's kind of hard for us to know which is which, because that's a pretty wide range of wind speeds that would cause those two things. So, sometimes the MPing reports are a little harder to decipher. With hail, they're pretty good because you can get an exact size. But with respect to wind damage, a lot of times those aren't as helpful. So what is the name of that red and green radar? Okay, so yeah, that's a good point. I probably didn't point this out. So a lot of the stuff we were looking at in the presentation was reflectivity, where you're just seeing, how much energy is being scattered back, and that kind of tells you how heavy the rain is. The reds were pretty heavy rain, and the greens and blues were lighter rain. But what you saw with the red and green, that's actually a different product within the radar called velocity. So again, with Doppler radar, you can actually see how fast raindrops are moving toward and away from the radar. And so that kind of is what helps you see the motion within the storm. In addition to the velocity product, you can look at storm relative motion. So that'll tell you which way the raindrops are moving with respect to the storm movement. And that's what helps you see rotation within a storm as well. So for instance, if you downloaded like an app like Radar Scope, you would be able to get those velocity products as well as the reflectivity with that. So, and pretty much most of your radar apps, I would say, will have that ability. It's not any sort of secret data or anything. It's all out there and it's all for public consumption. So it's more just about knowing where to find it. And yeah, pretty much most of your radar apps that you download on your phone, you will have that. And a lot of them are free. Some radar apps you may have to pay a subscription or whatever, or a one-time fee, but a lot of that stuff is free. So again, we're the government Department of Commerce, so it is funded by taxpayer money. So, but it is a good service that you get back out of it with severe weather warnings and watches and radar data, satellite data. The satellite data we have now is amazing. We really are pretty lucky. And I know sometimes, it's fun and easy to joke about forecasting and, the meteorologist is always wrong, that sort of thing. But if you think about it, I mean, there's a lot of times where we know 7 days in advance pretty good that we're going to have a pretty strong storm system. And that's pretty incredible if you think about how big of an atmosphere it is and how much things are moving around, that we can see a storm system 7 days out before it even develops with model data and things like that. So yeah, so really, for the pretty good bang for the buck with respect to satellite and radar data and model data. All right, so is there a source where someone can get the alpha tables you guys use? I'm not exactly sure what you mean by alpha tables. I'm not sure if you're talking about like color codes with the radar data. I guess I'd have to be more specific on what exactly you mean by that. With respect to radar color curves, Allison House is a good source for different color curves. So let's see here. So yeah, somebody else asked, will this be replayed? Yes, we'll put it on our YouTube channel and provide a link via social media and probably on our webpage too. Guts or stupidity. I guess that's referred to maybe getting too close to chasing in storms. Yeah, yeah. I was gonna say if you've got debris raining down around you, that might be bordering on the latter rather than the former. So, or maybe a little bit of both. What is the risk for big weather Monday night and Tuesday? So I did not forecast today, but I looked at it yesterday, and it looked like Wednesday was another risk for severe weather next week. It looks like maybe though there was a warm front lifting north across our area Monday night into Tuesday, and I saw a little surface low that kind of tracked along that, and that can be a little bit of a sneaky setup. So we're not out of the woods for Monday night or Tuesday. At the time I looked at it yesterday, there was some uncertainty about where that warm front was gonna set up, but it looked like it'd be close to our region, or maybe just to our north across central or central Indiana, central Illinois. But yeah, basically early to mid next week, we're gonna have to be on the lookout for another couple rounds of, at least one round, maybe 2 rounds of severe weather. Can I tell the direction of a storm on the ground and thus where to spot it safely? Okay, so that's a good question. One way you can kind of tell is if you just kind of stand and look at it for a minute and kind of just visually see which way it's moving. You're also going to still have to know, which way is north, which way is south, which way is, east and west to get your own bearings. But, just like, with phones, I know you can get a compass app on your phone very easily. So that can help you at least get your bearings and then kind of tell which way the storm is moving, with respect to where you're at. Another way is just to have a radar app, because a lot of these radar apps, they'll actually tag your location. So they'll show you where you're at with respect to where a storm is, basically using geotagging, using GPS to position where you're at. And so that's another good way, is just look at a radar app and see where you're at with respect to that storm and which way it's moving. I probably should have shown an example of just, like one basic one like radar scope, how it shows you where you're at with respect to a storm. But if you Google that, I'm sure you can get a quick image to see that. But yeah, another way you can tell which way the storm is moving just by visually looking at it is, again, if you look at that anvil, and if you look which way that anvil is spreading out downstream, that is going to be which way your upper level winds are pushing. And that's usually going to play a pretty big role in driving which way that storm moves. So you can kind of tell which way the storm is going to move if it has an anvil, which way it's spreading out downstream. That would be another way to visually get an idea. I always told people, if you're looking at a tornado on the horizon and it's not moving left and it's not moving right, but if it's getting bigger, then that means it's coming right at you. So I guess if the storm is, not moving left or right as you're staring at it, but it's getting bigger, then that probably means it's coming right at you. So, but good question. Okay. Okay, so I was wondering where one would find the handouts. So on your little interface here, there should be a tab that says handouts, and it says 4 out of 5. Hopefully you can find that, and they all should be there. You should be able to click on the link and then download them. I don't know if your screen is exact same as mine, but on mine they are there. So hopefully you're able to find those. If not, I'm sure you could email us or reach out to us and we could get them to you one way or another. So besides looking at radar animation, okay, wait, I already answered that question. Okay, moving on. Will there be a test? No test. Again, yeah, I think we used to have like a quiz or whatever at the end of some of our basic spotter. But for this is just, from what I could tell, most everybody sat through, the entire 2 hours and 15 minutes. And again, hopefully we learned a thing or two. And so yeah, just your, your willingness to be here for that long and to take it all in and ask good questions at the end. I think that more than serves the purpose of a test. So we appreciate your interest, as much as we enjoy doing this. So, okay, moving on. Yep, you're welcome. And again, thank you all for logging in as well. Yes, there will be access to it later. Again, hopefully on YouTube will probably be the best way. We'll put it on our webpage, a link to it, and then we'll probably put it on social media as well. So what can be used to identify derecho events and the direction a derecho will take? All right, so that's a really good question. All right, so for a derecho, here's what you need. You need extreme instability. So when we were talking about those values, 4,000 plus joules of CAPE, so you're going to have a very large, remember we talked about the fat area of the sounding, you're going to have a very large fat area in the mid-levels. So you also need pretty strong wind shear, probably 40 to 50 knots of wind shear. So the problem with derechos and why they're so rare is because it's really hard to get extreme instability in conjunction with wind shear that strong. Because to get extreme instability that strong, you need to probably be in like the mid to late summer months. And that's usually when your wind shear is a lot weaker because the jet stream is displaced a lot farther north. So, but to get in extreme instability, you're talking, days where it's like 90 over 75. So it's incredibly hot, incredibly humid. And then you get a disturbance in the jet stream that creates that really cold air in the mid levels. And that's the perfect scenario for a very extreme type of unstable environment. But again, you've got to have that wind shear, because what happens is once you get the storms to develop, there's so much instability that it just turns into a whole bunch of storms and convective clusters. And and it becomes very messy very quickly. But then what happens is as those storms kind of start to put out their downdrafts and their outflow, they'll develop this pool of cold air that starts to push the storms, and then they start to organize in a line, and then you still have, and then what they're doing is basically that cold air, we call it a cold pool, will get going, and it'll continue to push those storms into that very extremely unstable air mass. And it's kind of like this system that feeds off of each other, where there's enough shear and there's enough instability, and there's a very strong cold pool that gets going, that just keeps pushing that storm downstream, and it'll accelerate, it'll bow out, and you'll get widespread 60 to 70 to even 80-mile-an-hour winds with a derecho. So a lot of times when that happens is late summer, in a northwest flow type of a pattern. So you'll have northwest flow aloft. And again, you kind of have to be on the edge of an upper ridge where you have really strong and extreme instability. So that's a good question. Again, derecho events are rare just because of how rare it is to get those ingredients to line up, but there's no joke when they do get going. All right, so that was a really good question. Yeah, you can rewatch it. Again, we'll put it on YouTube, probably, maybe even tomorrow if we can get to it. Tomorrow's going to be a busy day because of the weather we have coming, but hopefully we'll be able to get that done tomorrow. And again, we'll put it out on social media and on our webpage, a link to YouTube. So good question. I saw one other question that I wanted to answer. Oh yeah, so how do we get the certificate? Just in case you didn't hear, so what we're going to do is we're going to send out an email. It says the next day, so everybody that was on here is going to get an email. I'm guessing probably tomorrow evening, since it may just be full 24 hours. But just wait for that email. It'll have a link in it. You'll fill out a brief form, and basically then it will send you an advanced spotter certificate via email. So I know we've done it for our other basic talks, and I haven't heard of any issues, so it should work out okay. But yeah, that should be the way you'll get it. And if you don't get it, just reach out to us, and we'll help you get that taken care of. As far as the slide set, I'm trying to think. We'll probably just do it with the recording. I don't know that we're gonna actually send the slides anywhere because it's 112 slides. So we did cover a lot of material in that 2 hours and 15 minutes, and that's a huge file. And there's just no way we could probably really distribute out a file that large to that many people. So we'll probably just put the recording on YouTube is going to be the best way, and then you'll have access to them that way. I have the link from the basic class. It has the option for advanced. Will that work? I think are you talking about the link to the, well, if you have the link from the basic class, it's probably going to send you a certificate that says basic spotter training. So if you really want it to say advanced, you're going to need to wait for that link tomorrow. So that's probably the difference there with respect to that question. Is radar scope better than LEX 18? Okay, so one thing you need to know, so there's tons of different radar apps out there, and it's actually not different radars, it's all the same radars. I mean, there are only so many radars across the country, and almost all of them are owned by National Weather Service. And some of the TV stations do have their own radars. I think LEX 18 may have their own radar. So for that area, if it is a radar that's sitting in Lexington, then yeah, that's going to probably be a little better because it's closer to the storm and the radar beam isn't as high off the ground. But in general, radar scope is going to give you almost every radar there is, not only the Doppler radars that the National Weather Service owns, but also your terminal Doppler radars that are FAA owned as well. So yeah, but that's not to, I mean, everything they show you on TV is still going to be the right data and the data you want to look at and pay attention to. It's just a lot of times it's the either the Weather Service radar or the FAA terminal Doppler radar. But I do think LEX 18 does have their own radar, but not every TV station does. So that's a good question. Why does it thunder when we have bad snow days? I think I maybe already answered that. Just a slide later. There's a thank you, you're welcome. Has a photo of the Brandenburg tornado. April 3rd, 1974, the super outbreak. The Brandenburg tornado. We have several photos of that tornado here. Actually, I have a guy that's right outside of my door that would probably know the answer to that. So give me 1 second. I will ask him. I'll be back in 10 seconds. Hey, Tom. Has a photo of the Brandenburg. Okay, so Tom, who is our resident climatologist and tornado history expert, says there has not ever been a photo that he's known of that has surfaced of the Brandenburg tornado. We do have photos of it when it was closer to Louisville and in this area, but not when it was in Brandenburg. So good question there. Okay, so yeah, helpful for you and your son, amateur radio operators. That's great. Yeah, amateur radio operators have been a big source of storm reports over the years. So we appreciate everything you all do for us and for the community. You know, in all this era of technology and cell phones, it's still cool to see the radio operators communicating that way. So we appreciate you all. Yep, you guys are welcome. Like I said, I enjoyed it as much as you guys probably did. Again, it's kind of cool to talk about some of this stuff. Okay. So again, session recording should be available in a couple days. Hopefully, we'd love to review again due to dense content. Yeah, I agree. I'm sorry, that was a lot of material to cover, but yeah, we'll make it available so you can watch it as many times as you want on YouTube, and hopefully, again, watch it a couple times and you'll probably be able to digest it a lot better. Do you think we'll see a chance of stronger supercells developing to the west around Western Kentucky and tracking the east towards Louisville and Lexington? Yeah, I tell you what, I think it's going to be mostly a linear type of a storm system to where maybe initially as the storms develop, you'll get some supercells, but a lot of times then it congeals more into a line. Now you could get some embedded supercells within that line, but I think your bigger threat for tornado is probably going to be those little brief spin up QLCS mesovortex tornadoes that we showed several examples of. You know, out to the west, definitely a better chance for some supercells and, you know, those types of tornadoes. But I think the further east you get, the better chance is going to be for those brief spin up tornadoes. And again, as we kind of showed, that instability really diminishes the further east you get and the deeper into the night you get. So just how far east that goes, whether it's the I-65 corridor, you know, Louisville down to Bowling Green, or whether that threat does exist all the way to Lexington. You know, based on that sounding we looked at, I'm not sure it's going to be as big of a threat over in Lexington, but you know, there's still 24 hours we got to get through, and you know, data can change a little bit from here to there. So, got to still pay attention. So, okay, yeah, appreciate the feedback. Yeah, thank you again. Thanks for attending. Russell County, we are far from the radar. How difficult is it to detect rotation closer to the surface? Yeah, so that's a really good question. And unfortunately, yeah, down in Russell County, you guys, and I'm just being honest here, the radar beam is 8,000 feet off the ground by the time it gets out there, because basically that radar beam rises with height. And it is tough to see low. I mean, we basically can't see low level rotation. We can see, you know, low to mid level rotation of storms, and a lot of times we actually use Nashville's radar to see you guys, and even Jackson's out there. And so yeah, in a perfect world, we would have you know, slightly better radar coverage. But I know we've got a great spotter network down there in Russell County. I know Daniel Wilson Storm Alert Center has a really good network and is a good source of information down there. So, you know, any reports you all get as spotters, if you pass that along to him, I know he can get it to us. In fact, is that him asking that question? That might be, I think I see your name, Wilson, there. So, but yeah, no, that's a really good question. Yeah, and unfortunately, you know, overall, east of the Mississippi River, we have really good radar coverage, but there are a few spots that just don't have quite as good of coverage. So, but then that's just why it makes spotters that much more important. So good question there. Is there anything I can take after this class to learn even more? Yeah, there is. So Comet, C-O-M-E-T, has tons of weather modules that you can take. So those are available. I think you may may have to get access to it through some academia. So if you're a student, that's one way. I can't remember if you can just sign up for those modules as the general public. There's other things you can do. I know, let's see here. I'm sure there's probably just, going online, there's probably all sorts of different weather modules you can look at through YouTube or just Google searches. There's research papers, there's published research papers. If you really want to get into some of the science and meteorology of some of this stuff. As far as the Weather Service goes, I haven't really seen much beyond advanced spotter training. We do offer different types of training. We offer training like kind of to get ready for situational awareness with respect to outdoor events. We call that event ready training. And that kind of helps you gauge storm motion and storm speed to kind of basically know how much time you have to evacuate folks from, whether it be a state fair, or county fair, or festival, things like that, outdoor music concert, things like that. But as far as, meteorological training and with respect to severe weather, this is probably the most in-depth you can find from the Weather Service. But Comet is a great resource if you can get access to those modules. And another thing, if you want to read a lot about this, so there's a website called theweatherprediction.com. It's put together by meteorologist Jeff Habe, and he calls it Habe Hints. But he catalogs all sorts of weather phenomena, not just severe weather. I mean, he goes into winter weather, and you can really learn a lot about forecasting and weather patterns off of his. It's a very comprehensive resource, and he's a very good forecaster that put it together. So yeah, it's called theweatherprediction.com. Jeff Habe. I still use that in case if there's a theory or something I need to brush up on, or a quick rule of thumb that I need to brush up on. Sometimes I still go back to that website and kind of re-educate myself. So yeah, there's several resources out there, and again, just looking around, you can probably find quite a bit. And quite honestly, just taking different Weather Service offices spotter classes, because we don't all put them, there's no cookie cutter presentation. We all kind of do something a little bit different. So, Wilmington's maybe slightly different than ours. Indianapolis is maybe slightly different than ours. And then shoot, if you can somehow get access to, say, some, office out in the Great Plains, they might do something quite a bit different. And, you can pick up little tidbits with each presentation you watch. So good question there. Yeah, again, appreciate you all as well. I had quite a bit of fun doing this. So yeah, somebody asked, good class, you guys going to do more of these? If we got 300 some people registering and 200 plus that stayed on for 2 hours and 15 minutes watching this, I think we'll try to do this every year. We might try to change up the material a little bit too, so it's not the same thing. But it's also complex enough that it might be good to review it every year. The more we review it, the more we can kind of get it burned into our brains. So yeah, and maybe we can add a different case study each time. That way, we apply what we learn to different scenarios. So yeah, I think with a response like this, I'm pretty sure we can probably do 1 or 2 of these a year to go along with those basic spotter classes. So okay, so let's see here. K4 KJQ Lexington Ham Radio Club's repeater 146760. It will most likely be the repeater for storm info. Scott County beyond. Okay, so that's good info for any of the ham radio operators out there. I might write that down too, because again, during the big events, we can bring people in to actually work ham radio for us, but because of FCC rules, we cannot do it while we are working. And quite honestly, we usually need the bodies here, working, rather than we don't have extra ones to contribute to that. So yeah, but that is good info that we can monitor that if we have the ability to do that. So I will write that info down. Thank you for that info from the Lexington Ham Radio Club. Okay, well, our spotter number beyond the certificate or the email, I never received one with the basic course. Okay, so I know in the form, as you fill it out, it asks you for a spotter number. So I'm pretty sure if you put your spotter number on there, it will put that on your certificate. I'm not 100% sure. That could be just a way that we're tracking, but I'm optimistic that it will. If you don't get your advanced one after the link comes to you in a day or so, let us know and we'll see what went wrong. But yeah, as long as you fill out that form, you should get it. Okay, and yeah, thank you for the compliment. Moving on here. Okay, so would you guys ever consider doing a course on radar scope with tier 2 functions enabled? It was a great class tonight. I'm sure you'd understand all the user functions and display data parameters. Okay, so that gets a little kind of dicey for us. I don't know that we can really do a presentation on a specific piece of software, because we can't really promote one over another, being the government. That's kind of a government private sector conflict of interest. So, if we offered a class, what it would be is it would kind of be like an overall kind of maybe overview of different, radar softwares, but we can't promote one over another. So I don't think we could offer a specific class, directly related to radar scope, if that makes sense. But I'm sure there's probably maybe YouTube videos online where people go through that type of stuff that would be pretty reliable. Maybe that would be an option, or just even like a blog or something where people really get into, how to use those functions and displays. So that might be an option. Yeah, I know that would be a useful presentation, and there's several of us here that could probably give that, but just from a government private sector standpoint, we can't really do that, unfortunately. So yeah, that's probably as much as I can answer that question. Yeah, you will get your certificate. So Avery with Heart Emergency Services County. What model characteristics or soundings are associated with a derecho event? Okay, I may have answered that already. Maybe for the next one, we'll show you, because even some of the soundings I showed you for this presentation, they weren't really that unstable. I think there was some moderate instability to maybe even strong instability on one of them. But one of these times I'll get out a sounding that shows like extreme instability and show you what that looks like, and then maybe show you the derecho or whatever that followed that environment. So yeah, there's lots of things we can do with this presentation where we can have a different case study each time every year. So yeah, it seems like there's some interest in derechos, so maybe we'll go that route for next year. So good feedback there. Yep, you all are welcome. If we are noticing something interesting on radar, should we report that? I mean, usually we have at least 2 or 3 sets of eyes on radar, and I mean, most of the time somebody's going to notice that, if not all the time. I guess you could, yeah, it's always worth the call, but in general, we're usually pretty busy in those scenarios. So, unless it's like a report, which, is really what we need. That's the main thing we're looking for, not to tie up the phone lines. But yeah, if you notice something interesting, sure, feel free to call, and then maybe we can match that up with what you're seeing on the ground or whatever out there. And it's always good to have a set of eyes to match with what we're seeing on radar. So yeah, go ahead. What does the omega mean on the left side of the sounding in DGZ? Okay, yeah, so that's a really good question. So omega is a measure of vertical motion. And it's different than like your instability. Omega is usually that more large scale, slower lift that we talked about with like winter storms. It's the large scale or synoptic setup that we talk about. So ahead of a jet stream, you'll get lift through a pretty deep layer, and that's measured in units of microbars per second, and then it's displayed as omega. So yeah, that's a really good question. So yeah, anywhere where you're seeing omega, it's usually lift. Now, back from the classes that we took, negative omega was actually vertical motion, and positive omega was downward vertical motion. So it does get a little bit confusing if you're looking at a negative microbars versus positive. And some soundings display it differently than others, but in general, you're always going to have upward vertical motion ahead of a big strong storm system, and you're going to have downward vertical motion under like a ridge of high pressure in general. So, but that's a really good question. Good observation. I believe in this one is displayed as, yeah, so negative is actually upward vertical motion, is what it looks like here. And that's that's pascals per second, which is a measure of pressure. So basically, that's a very, very slow rising type of a thing, on a much larger scale than what we're talking about with instability. But yeah, you definitely get upward vertical motion ahead of those systems. Okay, so let's see. In soundings, we talked about LCL, and we may. Okay. So I don't know if that question got finished or not, but yeah, we talked about the lifted condensation level a little bit. That's basically going to drive where your cloud base starts, or where you start to see clouds, and that's kind of where that air parcel becomes saturated. So really, what you want to look at LCLs for with respect to like parameters and severe weather is anything under 1,000 meters is much more conducive to tornadoes. As long as you have other parameters in place, that are supportive of tornadoes. Once you get above 1,000 meters to 1,200 meters, you can still get a tornado, but it's pretty, more of a ropey type of a tornado, very thin. A lot harder to kind of make contact with the ground. You can get funnel clouds in that situation. And anything over 1,200 meters, it's going to be very unlikely that you're going to get a tornado. So yeah, the lower the LCL, the better chance for tornado when in the presence of other parameters that support a tornado. So good question there. Will the convergence between the two systems pass over to Louisville based on projections, or would the two pressure systems bounce off of each other? So generally, with the pressure systems, they're always kind of moving. They don't really necessarily bounce off of each other. They actually kind of, one will displace the other, or vice versa. So yeah, they're not really going to bounce off each other. And I think the low track is pretty well set in stone with the system. It's going to track from, the upper Midwest into the Great Lakes. So I don't know that we're going to dodge a bullet. The only way we can really dodge a bullet with this is if we just don't have the instability and we just get the gusty winds outside of storms and, just the rain with the storms, but we don't actually get any severe. So that's our best case scenario. We're definitely at least going to get some weather tomorrow, and we're going to get gusty winds regardless of whether they come from thunderstorms or not because of how strong that low pressure is. But yeah, there's not really much hope that it's going to like bounce off of each other and then we're not going to get anything at all, if that makes sense. So good question though. Let's see here. So we sometimes get storms that come out of the east-northeast instead of normal west-southwest, and they always seem to be much stronger than normal pattern. Is there a specific reason for this? Tell you what, I don't know of too many like true-blown like severe thunderstorms that are going to come out of the east-northeast. Sometimes what you can get is an upper low that kind of sits and gets stuck over our region, and if it's kind of centered just to your south and west, then you'll get storms that'll come from the east or the northeast as they rotate around that upper low. Those are the types of storms that will draw off some of that Atlantic moisture that we talked about, the Atlantic Ocean. So you can probably get some heavy rain, especially since those are usually pretty slow to move and you just get repeated rounds of rain. But to be honest with you, I don't know of too many situations where I've seen like east to west or northeast to southwest moving storms that produce severe weather. Yeah, but yeah, from a rainfall and repeated rain standpoint, yeah, you can definitely get that in that type of a pattern. It's a good question there. Let's see here. Why does some thunder seem to last forever, but other times it dissipates quickly? Yeah, that's a good question. There's been times where I've even noticed where it seems like the rumble of thunder just continually goes on for like 10 seconds or, and other times it's just a quick clap of thunder. I think a lot of times that has to do with one, how far away it is, and two, sometimes if you do have an inversion in place in the lower levels, like you still get like the air parcels rise enough where you get a thunderstorm development above the inversion. It's called an elevated thunderstorm. And so sometimes I think that if you do get a thunderclap and you have an inversion in place, sometimes I think it propagates down below that inversion, almost gets trapped. And so you get like longer rumbles of thunder. Whereas if it's just like a lightning strike, that comes and goes, then, it can get out of there pretty quickly and it, the sound dissipates pretty quickly. That's just me guessing, quite honestly. I don't really know what kind of science is behind that, or I'm not really, wouldn't consider myself an expert on that. The other thing is you've got positive lightning strikes and negative lightning strikes. So generally negative lightning strikes are just a quick little strobe, you know, 1 or 2 flashes and it's over. And those are, you know, much more brief. And then if you get a positive cloud to ground CG lightning strike, those are like several strobes, and it'll sit there and flicker for a second or two. Those are usually more intense lightning strikes, and they will, you know, actually cause more fatalities. A positive CG strike will over a negative, and I think maybe that can create more louder thunder as well, and more kind of lingering thunder, just because you get several strikes within that channel that's briefly created. So that's possibility as well. But that's a good question. I wish I could answer it better. But I've actually found myself wondering the same thing at times, especially when I'm trying to sleep at night. So am I wrong in using VIL to identify large hail? No, VIL is a good indicator of basically what it is it's vertically integrated liquid. So what you're looking at is, you know, as we step through the depth of that storm, you know, we looked at the hail core aloft. And so what VIL does is it will show you how much concentrated moisture you have, you know, with that core, basically through the depth of the storm. Now, it is kind of I don't want to say an old school product, because we do have dual polarization now that we can, you know, see and identify hail a little bit better. But yeah, no, a maxed out VIL density will a lot of times be a good indicator of hail. Now, you're not going to generally know how large that hail is. There's other factors too, like how deep the melting layer is. So it's not going to be a, you know, a be all end all that every time you see, you know, a maxed out VIL density that you're going to get hail on the ground. But I just remember from the early days in my career, 80 was the max VIL density, and it was a brown color. And so we would always say, if VIL is brown, hail is coming down. So, you know, if it is maxed out, there's probably a good chance you're at least going to see small hail and maybe big hail. But yeah, there's other factors that are going to kind of, you know, play into exactly what you see at the surface. But good question. All right, let's see here. Moving on. We may have talked about it, but what is the LFC and how could that impact thunderstorms? All right, so the LFC is the level of free convection, and that is actually going to be, sometimes it's just above where your LCL is, but basically that is the point that that parcel of air will rise on its own without any other thing, you know, aiding it. So to get the parcel to your LFC, you need some sort of lift. Like, again, we talked about cold fronts, you know, jet stream disturbances, short waves, things like that. But once that parcel gets to that level of free convection, and again, that's basically where that dotted line that we were looking at on the soundings, where that is going to always be warmer than your environmental temperature. And basically, you know, those mid-level lapse rates will cool off quicker than the air parcel cools as it rises, because of that set moist adiabatic lapse rate. So yeah, once it gets to that point, then that parcel is just going to go, and it's not going to stop until it hits that warm air. And again, that's that tropopause up at like 40 or 50,000 feet. So yeah, if you can get an air parcel to that level of free convection, that's when your thunderstorm begins. But again, the hard part is getting it there, because you have caps, you have inversions, and you have, you know, sometimes you just don't have enough lift to even get it there. So really good question. I probably should have spent more time on the LFC. But yeah, really good question. Okay, so I've noticed that squalls have a tendency to break near or around rivers. If that is the case, if so, can you explain what causes that? So yeah, in local areas, a lot of times people will claim, you know, that in, you know, a river or a body of water sometimes will disrupt storms. And, you know, in general, especially with like a squall line, which is a large scale feature that's usually driven by a, you know, several 100-kilometer, you know, wide cold front or whatever. A lot of times the storm system is bigger than any one river or body of water can really influence it. What I will say is that you get a lot of terrain effects that can be, you know, on a small scale that can maybe influence storms in a certain way, maybe briefly or whatever. You know, if you think about the plains out, you know, where the land is flat, there's not as much surface roughness out there. But if you get in like a hilly terrain environment, there's kind of some friction and surface roughness that can, at least disrupt some of that low level flow a little bit into the storms. And we know how important low level inflow into a storm is, to feed that updraft. So, in general, we'll say that, most of the time the bend in the river or, local terrain effects aren't enough to really influence a large storm system, especially like a well-organized supercell that's got its act together. But I think it'd be crazy to not say that you don't get some very small scale local terrain interactions that can maybe disrupt storms from time to time, or maybe even strengthen them. If you think about terrain funneling, if you got a downburst wind and it kind of gets funneled in between, two pretty steep hills or whatever, you can actually intensify the wind in that situation. So yeah, and each local area is different. People that live in an area for a long time, every spotter talk I give, somebody will come up to me and say, yeah, I noticed this about my area, storms tend to do this. And I tend to believe those people because, like I said, they've lived there their whole life and they observe what happens. It's hard to deny it, really. So good observations. Let's see here, what else do we have? Why isn't there a water spout warning? So in general, number one, we don't really get water spouts around here. Any tornado that we have that's on the ground that crosses, say, the Ohio River, the Kentucky River, or whatever, we're still just going to call that a tornado. I mean, technically, I guess it's a water spout while it's, out over the water, but it's not going to be over the water long as it's moving along. So, and I know that, like if you work at a coastal National Weather Service office, they'll issue, special marine warnings for water spouts and things like that. But in general, where you get water spouts, most of the time, other than maybe a few boats around, there's not really any population. And especially if it's like just a small boat, they're not going to really have much of a way to receive that warning anyway. But I know that the Weather Service does issue statements and or marine warnings when they do know a water spout's there. The other issue is those are usually pretty shallow circulations. So they may not always be detected on radar, or they may be too brief or too weak, because that is a slightly different process that creates a water spout versus like a supercell tornado. So there may be a lot of times where they just don't know about it, so no warning is issued in that sense. But yeah, if they know about it, they will issue a statement on it. So good question there. What's the coldest temperature a tornado can form? Yeah, that's kind of a tough question to answer. In general, like we've seen a couple of cool season tornadoes develop in environments where you're talking about a temperature of like 55 over a dew point of 50. In general, a good rule of thumb is you really want your dew points up, 55 to 60, and your temperature is 60 to 65, at least for most tornado environments. But every once in a while, you can just get just enough instability if you've got a very sheared environment that, even 55 over 50 isn't completely unreasonable. I think that one event I showed December 6th, 7th, right before the big December 10th, 11th outbreak, we had dew points that were in the low 50s with that tornado, which, that was a pretty tough environment because it was a very, very marginal environment. But like I said, it just does not take much around here, and you can still get stuff. So it's a good question, though. So, but let's see here. Thanks. I've done several basic trainings and elite spotter training with Paducah, and now this was the best one yet. Okay, well, I appreciate that that compliment. I put a lot of time into this, and yeah, I hope everybody enjoyed it. I'm happy to see the amount of people that attended it. So yeah, we'll try to do it again next year, and we'll change up some of the material, and we'll do it again. So hopefully we'll see you next year. What is the effect of INSO neutral? Okay, so what you're talking about with INSO neutral is INSO is El Nino Southern Oscillation, and that is one of the many teleconnections that drive our global weather patterns. So INSO, El Nino, and La Nina are certainly probably the most popular ones that you hear, a lot of mainstream media and things like that. But there are several different teleconnections. You've got the Pacific Decadal Oscillation, you've got the MJO, the Madden-Julian Oscillation, you've got the North Atlantic, the NAO, which the NAO and the AO, the Arctic Oscillation, they all kind of drive a lot of our winter patterns. But so what we've been in for most of the winter was a La Nina. And if you go from a La Nina to an ENSO neutral, usually I'll say this about La Ninas, especially as you get into late winter, early spring, that is usually not a great, well, here, how's the best way to say this? It's a bad pattern with respect to severe weather. In other words, you're going to get a lot of Dixie Alley outbreaks and sometimes into the Ohio River Valley with a La Nina pattern. So that is that, and we've kind of already seen that this late winter, early spring. We've seen, we saw the Mississippi tornado just last weekend, and we've had a couple of weather events. We're going to have one tomorrow, and that's again, La Nina is kind of the type of pattern that drives that. But as you transition from La Nina into kind of more of a neutral pattern, so that's not La Nina and that's not El Nino, that's kind of right in the middle. That will shut down probably a lot of those Dixie Alley type of events, and I believe we'll actually get warmer over the eastern CONUS, and it would shift more of a trough west ridge east type of a pattern. So that could go into an ENSO neutral into the spring months. That could set up a pretty decent and active severe weather season for the Central Plains, Southern and Central Plains. I know I've read that could be a possibility this year. So, but on my day-to-day jobs, I generally am 7 days out. So I don't have as much knowledge of your overall large teleconnection patterns. But in general, if we can get out of La Nina sooner than later, that will hopefully shut down the wet and mild pattern that produces severe weather late winter, early spring. So good question there. Moving on. Let's see here. So what are some of your favorite, most used resources for monitoring weather and best ways for us to share or report it? Okay, so for monitoring weather, some of those storm prediction sites storm prediction center sites that I showed you, I really like. Those update every hour, so you can kind of keep up with evolving environments as you're looking at those weather parameters. So that's good for monitoring real time. The Kentucky Mesonet, so it's www.kymesonet.org. That's basically a very dense network of surface observing stations that'll measure wind direction, wind speed, precipitation, temperature dew point, solar radiation, even on some of the sites. So that's a great way. I mean, we're really lucky to have that here in Kentucky. Not every state has a Mesonet. That's great for monitoring real-time weather. You can, as a cold front's passing from east to west across Kentucky, you can really see, sharp temperature gradients, or vice versa. If you've got a warm front lifting north or something across the area, you can really see the temperatures warming from south to north. We use that a lot in the winter just to see your freezing line, with respect to to freezing rain or sleet or whatever, or even this rain snow line. So that's yeah, those are probably two of my favorites. As far as best ways to share or report it, yeah, I mean, best way is probably just to call the spotter number to report any sort of damage or hail or wind or whatever that you come across. If you have social media, then to follow us on social media. That's another good way to reach out that we'll probably see pretty quickly. So those are two of the best ways. If you're an emergency manager or some sort of law enforcement, you can follow NWS Chat. You can get signed up that way, and that's a good way to report weather information as well. So good question there. So let's see here. Should we pay attention? On the sounding example, what's the difference between surface-based CAPE, mixed layer CAPE, most unstable CAPE? Which one can we pay attention to when checking CAPE? All right, so that's a good question. So in general, I think mixed layer CAPE is going to be your most representative for most situations. Most unstable CAPE is generally going to be good to look at when you have an elevated thunderstorm. So in other words, you've got enough lift to get that air parcel above or actually initiated above an inversion. So it doesn't actually have to break through the inversion. It actually just initiates above that inversion. And there will be a stable layer. So in that situation, surface-based CAPE won't really show up and mixed layer CAPE will show up. So you need to look at most unstable CAPE. A lot of times you'll get elevated thunderstorms to the north of a warm front. So look at most unstable Cape if you're going to have thunderstorms to the north of a warm front. Otherwise, you're going to want to look for surface-based or mixed layer Cape. There's not a whole lot of difference between surface-based Cape and mixed layer Cape, other than that mixed layer Cape will lift that parcel basically anywhere from the best location throughout your low level, what we call boundary layer or mixed layer. Whereas surface-based Cape will raise that parcel straight from the surface. So sometimes you can get some pretty big numbers with surface-based Cape, but in reality, a lot of times your realized instability is a little less. So I really like to use mixed layer Cape for most instances, unless it's elevated thunderstorms, then I use the most unstable Cape. So good question there. Okay. Love to learn more about how to read and interpret these charts. Yeah. You know, there's lots of research papers out there. And again, there's some of those comment modules, if you can get access to those, and maybe just full-blown YouTube videos from other weather enthusiasts. Just be careful, you know who your source is on some of those. Make sure they are kind of an expert in the field. Sometimes we do get some know-it-alls out there that kind of have their own ideas about things, and you kind of just want to be careful who your source is. But yeah, there's plenty of info out there. You just kind of got to know where to find it. Future trainings, yeah, like I said, I think we're going to do this every year, and we'll try to change it up a little bit every year, so to keep it interesting and fresh, but still kind of hit a lot of the main points. So yeah, as long as there's good feedback and interest, we'll keep doing it. So, okay, moving on. Okay, my son asked the following question, but unfortunately laptop died, and hold on. Sorry, I lost my spot. Huh, I lost that question. The question, draft has to be the same temp as it goes higher, but doesn't the atmosphere get colder the higher you go? So how does that work? Yeah, so I think I may have touched on this before. So the way it works is that air parcel will continue to rise as long as it is warmer than its surrounding environment. So, and you have to remember that that cool air in the mid levels is going to cool off faster than that air parcel will cool off faster. And so if that air parcel, once it gets to, you know, that environment, it's going to continue to stay warmer than its surroundings until it hits that warm layer of air aloft. So yeah, so even though it is cooling with height, it's not cooling as fast as what the actual environmental temperature is cooling aloft. I hope that makes sense. And so it does end up staying warmer than its surroundings. So it continues to rise. It's a good question. What direction is the best way to travel from a tornado? I always like to say south, because generally that's in the, you know, kind of if you travel north, you're basically going to be driving into the precipitation core and you won't be able to see a thing, and you'll be driving in heavy rain, so you probably can't go, you know, a normal speed for fear of hydroplaning. And so the best way is south. Is really kind of a good escape route. A lot of times you won't have many storms, you know, as many storms to the south. It kind of depends on the setup, but you know, how many other storms are around. But a lot of times in your inflow region of the storm, you won't have as many other storms. So yeah, in fact, you know, chasers, a lot of times if they stop to park to observe a storm, they will point their car in a southward facing manner. That way they can just get in it and quickly get south if you know, the storm starts to bear down on them. So yeah, south is the best answer in general, but again, you know, just make sure you're not driving into the path of the storm if you are driving south. Somebody said radar scope has MPing built in. If that's the case, I did not know that, but that's good info. So that's another, you know, a good perk of radar scope is not only can you view storms, but it sounds like you can send reports as well straight through the app. So The spotter number, it should be on your handout, but I also have it. Let me go back here, read it off to you real quick. It's all the way back at the beginning. I probably should have put it on the last slide as well. Almost there. Spotter number is 800-292-5588. 800-292-5588. It's the weather app from Eastern Kentucky, good to use. I'm not sure which app you're talking about, but you know, any of your apps from your TV stations are going to be a good app to use. They're going to have all the information you need, you know, watches, mornings, things like that. Probably some radar data access as well as satellite data as well. So yeah, I would think so. I'm not exactly sure what you mean by Eastern Kentucky, you know, who you're specifically referring to, but yeah, as long as it's from a local broadcast meteorologist, it should be a good app to use. So one person made a comment here, says MPing is only good for older version Android. So I do know it's been around for a while, and I don't know how well it plays with Apple versus Android and all that. But there's also a website online, the NSSL MPing website. So if you don't have an app or a phone, you can actually still probably submit a report through an actual PC or laptop or something through the website as well. Mark Adams says hello. Mark Adams, we miss you. I hope you're enjoying retirement. He's been living the dream from what I've seen. So good to hear that name. Do you issue warnings or watches for the NWS? Yes, I do. So yeah, there's basically we have 14 or 15 meteorologists here that pretty much in any given event, one of us will be the ones, watching the radar and issuing warnings. Now we don't issue the watches. Actually, SPC, the Storm Prediction Center, so the ones that give you all those severe weather outlooks, they are the ones that issue the watches initially. What they will do is they'll get on a conference call with us and we'll talk about the watch and where we want it. And, they'll make sure that they agree to. And then once that watch comes out, then we are in control of it from there. So then we can add counties or extend the time of the watch if that needs to be, if the threat's going to go longer, or we can cancel it early if the threat has diminished. But yeah, then once we get into warning mode, then that is all us. And again, we're using Doppler radar, environmental data, satellite data to make those decisions. But yep, any tornado warning, severe thunderstorm warning, those all come from us. So good question. Okay, so if you have the means to monitor wind direction, will you see a drastic change as the hook passes near you, indicating the potential tornado? Yeah, depending on how close you were. So yeah, you definitely would see the wind shift. You would initially probably get something like a southeast wind, and then a south wind, and then a southwest wind, and likely increasing intensity. And then as that rear flank downdraft kind of swings around and passes you, you would get probably more of a west wind and even maybe a northwest wind. I will say I've been standing in the inflow of a tornadic supercell. Actually, it was that one from 2009 that I showed at the beginning. And it was, I'm not kidding, it was probably 40 to 50 mile an hour inflow. And it was almost hard to stand as that updraft base was passing just to our north and we were in the inflow. So when I say inflow, it's not just 20, 30 mile an hour. It can be, especially with an intense updraft, it can be really impressive inflow. And so, and sometimes you can even tell that the storm might be strengthening if suddenly that inflow really increases. So that would be a good indication that things are about to start to get a little more interesting. So good question. Okay. Okay, so you're talking about alpha tables in regard to Gibson Ridge and the volumetric view. Okay, so I think what you're talking about is where we filtered out some of the velocity data or the reflectivity data to get different storm structures showing up. To be honest with you, it's a kind of a case-by-case basis, and I just have to, when I filter out, like that one where I filtered out the microburst that showed up really nicely, that was just a guess and check type of a thing where I would just played around with it till I got that to show up. So there's not one specific alpha table we use, but it's kind of just a case-by-case basis. If that makes sense, you kind of almost have to just play around with it until till you hit pay dirt and get lucky. So hopefully that helps. But you can, I tell you what, if you spend time with it, you can really kind of find some pretty cool things, you know, given the right storm and the right structure. So the velocity Q radar omega is very nice also. Okay, good comment there. Okay, let's see here. Look at SYN-H to forecast when storm systems will subside. Exactly. So SYN, it's short for convective inhibition, and that's basically another way to talk about capping or an inversion. So yeah, that's basically downward sinking air, which will, you know, inhibit upward vertical motion that you need for thunderstorms. So yeah, and when I showed you that example of looking at CAPE on the mesoanalysis, you can actually see SYN on that graphic as well. It's in like the blue hatched or blue shaded areas. So good observation there. Good point. I probably should have brought up SYN. But yeah, that's basically another word for capping or sinking air. If heat rises, why do air pockets cool as they rise? So let's see here. So what's happening is basically there's a lapse rate that the air parcel cools as it rises, and that's basically because it's condensating. So in general, yes, the heat will rise, and if you're talking like, you know, like a fire or smoke ring, you know, that's usually over, you know, 50, 100 feet, you know, pretty short distance, unless it's like a giant fire. But when we're talking about these air parcels here, yeah, that's basically it's not only cooling, but it's also condensating. So it's a little bit different process. Hope that makes sense. And, you know, in general, you know, for instance, like if you think about a hot air balloon, yeah, if you're heating that hot air balloon, you know, it's rising as well. So yeah, hopefully that answers your questions, but it has to do with processes related to moisture as well, and condensating and saturating. So it's not just the heat alone. Hopefully that makes sense, and that's what causes it to cool at the rate that it does, whether it be the dry adiabatic lapse rate before it's saturated or the moist adiabatic lapse rate after it's saturated. Okay, moving on. There's no tab. Is that, I don't know if that's in reference to the handout tab. I know somebody had asked about handouts earlier. If not, I'm not sure, because I can see it on mine, so I just don't know what you all are looking at from your end. Otherwise, I'm not sure what that's in reference to. Somebody said there wasn't one for basic training either. Huh. I don't know what to do about that. If you don't have access to the spotter handouts, we may just have to probably, anytime we have a spotter talk in person in your area, we'll definitely hand them out there. So that's probably the best way to get a hold of one. Maybe we can put some documents online that people can download. We'll see about that. We'll check into that. So thanks for bringing that up. Somebody else said the handouts are there. So I don't know, it could be depending on, you know, what system you're looking at this from. I don't know. Like I said, I can't see what you're seeing from your end. So, but some people say the handouts are there and some people say they can't find them. We'll look into that. Spotter number again is 800-292-5588. Yeah. Okay. Yeah, and if you want to reach out to us via email, we can probably send you the documents that way as well. Okay. Okay, moving on. What's the difference between negative tilted and positive tilted storms? Okay, so you're asking negative tilted versus positive tilted. I think what you're referring to is like a negative tilt trough versus a positive tilt trough. So a negative tilt trough a lot of times is pretty conducive to severe weather. And that's because you actually get better cold air advection in the mid levels. And like we talked about, you really need that cold air in the mid levels to create instability, especially if it's over top of warm, moist air at the surface. So yeah, a negative tilt trough is a little bit better for severe weather than a positive tilt, but you can get severe weather with both. A lot of times negative tilt may be more like a supercell type of a setup, whereas positive tilt a lot of times is going to be more like a linear system as well. So yeah, that's a good question. Is the reporting hotline listed on the handout national or just for Louisville? I think it's for local. So yeah, that 800-292-5588, that's our local spotter number. It is an 800 number, but it's local. So, and I think each office has a different spotter number. So yeah, you should be able to ring into the Louisville office if you call that number. So, what's this question say? Something about helping out with WHS 11 First Alert Storm Team as well with the NWS. So yeah, if you're reporting to them, that's great too. If you have a local media source that you want to report to, that's good because they can get that information communicated on the air, and then they can also relay that to us. So yeah, whoever you're reporting to, you know, if they're a trustworthy source, then that should find its way to us. So what is the best weather station available commercially that would provide accurate information? You know, they're all great. They're all great communicators. They all are in it for the same reason that we are, which is the protection of lives and property. And so I can't really tell you one over the other. What I would say is just, you know, whoever you're most comfortable with is who you want, you know, to follow. Because really it's about trusting whoever is giving you that information. But I can't tell. I mean, there's nobody would lead you astray. I mean, everybody is very good and very professional and good at what they do, and they're great communicators. So yeah, I would just whoever you are most comfortable with is the best answer to that. And we work closely with all of our TV markets. So yeah, we have good relationships, and we can talk. We chat in a chat room, so we're always bouncing ideas off of each other. So it's not, you know, a one-way street, you know, or whatever. There's always good communication. You're welcome. Yeah, again, enjoyed putting it together. Let's see. I took the basic a few weeks ago and filled out the Google form. Afterwards, I've never received a certificate. How can I obtain that? I'd tell you try and see if you get that link tomorrow and try to fill it out again and see if you get it. If not, reach out to us and we'll see if we can get you a certificate. You know, we're kind of using automation to help do this, and you know, some challenges can arise with that. I haven't heard of any major complaints or with people not getting them, but I imagine it happens from time to time. So we'll see if we can get it resolved. Have we ever thought about creating weather spotter window stickers for a vehicle? So maybe you're talking about like the Skywarn logo or whatever. I know they used to have things like that because I actually had one on my vehicle when I was in college. But yeah, I don't know that we really have that much anymore. I'm sure you could probably still find something online, maybe somewhere. But yeah, I don't know of us having any at the moment. Maybe that's something we can still get access to. We might look into that. But good question. Oh yeah, commercial drone pilot here to help you guys out. So yeah, I mean, right now we do have our own drones, but there for a while we did not. And so we were actually kind of reaching out to the public and, you know, anytime we went out on a survey with, you know, local emergency management, we asked them if they knew anybody that had a drone, you know, because like I said, that aerial view of damage does give you a different perspective and it makes it easier to survey and rate storms. So yeah, we appreciate you. If you ever know we're going to be surveying your area, feel free to reach out. We can always use that type of data. You all are welcome. Yeah, again, I really enjoyed giving it. So we'll try to do this every year. Should we check Storm Spotter or amateur radio if we are both? You know, I don't think it really matters. I guess whichever you're most proud of. So either will be just fine. If there's an option for both, then, and if it will allow you to do both, then I would do both. That way we know you have kind of both those backgrounds. But yeah, otherwise, just whichever you're most proud of should be fine. Okay, somebody said it's 85, 75 off the ground here in Russell County. Yeah, I mean, 7,000 or 8,000 feet, it's pretty high up there. So yeah, and this person says, I'm in Russell County, I get better resolution from the Nashville feeds. Like I said, when we're watching storms in your area, a lot of times we're using the Nashville radar. So that's really the closest and going to give you the best data for that area. But even then, it's still 7,000 or 8,000 feet off the ground. I knew that was you, Daniel. So that's our Weather Ready Nation ambassador down in Russell County, the Storm Alert Center. Good guy down there. So hopefully we don't have to go down there and see him again anytime soon. He had a pretty strong storm a month or two ago. So we'd like to see you under better circumstances. Where do we find our spotter number? So yeah, I don't know if you're talking about the like the storm reporting number, 800-292-5588, or if you're talking about an individual ID. I guess I'd have to get some clarification on what you're asking there. Let's see here. Hazardous weather and community risk is 0027. Okay, so that's just a comment. Moving on. Okay, so somebody said NWS Paducah is hosting an elite class for the person that want more. So I don't know, do they have basic, advanced, and then elite? If that's the case, then yeah, you might want to go to that. So that sounds pretty cool. I might attend that. So yeah, I would look into that if you could, if you're looking for more info. And somebody said would love to find out more of these other situation specific events. So yeah, what we'll do is we'll provide a case study or two that's new every year. That way we get to not just look at the same stuff over and over again. Because there, like I said, that was just one event out of hundreds and hundreds of possible scenarios. I know there was some interest in derechos, so maybe we'll focus on derechos a little more next year. Comment, yeah, somebody put a link to the comment, meded.ucar. So yeah, that's going to be really good stuff, and they're very good modules, and you'll be able to get pretty deep into the meteorology of things if you take those modules. So, and there's lots of them, so you can spend a lot of time doing it. So yeah, I would recommend that if you can do it. Okay. Do you all do any partnerships with the American Red Cross for emergency first aid and training that may be necessary after a severe weather event for this type of area? So yeah, we definitely consider the Red Cross as a core partner, in conjunction with emergency management, first responders, law enforcement, all of that type of stuff. So really the Red Cross is going to be, a lot of times it's going to be kind of your post-event recovery type of scenario. So sometimes we'll team up with them and do like weather radio programming or spotter talks, things like that, or just, safety booths and fairs and things like that. So yes, we definitely do have a partnership with them. They're a great resource, especially for the post-event recovery time frame, but also good for just, weather awareness as well. Okay, moving on. Somebody said, is the reporting hormone listed on the handout national or just for Louisville? I don't know if that meant to be hotline or what, but it looks like spell check got somebody there. Yeah, so I think that is a local number, so the hotline. Somebody provided a link to weather.gov/education. That's going to be a good link for more resources. So yeah, anybody that's looking for more info, there are a lot of resources out there. No Weather Partners has some modules on YouTube, FYI. So yeah, that would be another good one. I know another one is like Weather Brains. They'll do episodes. I don't know if it's once a month or once a week, but there's usually good guest speakers and topics that they cover on Weather Brains. So that would be another good series to follow. Looks like the elite spotter for Paducah is April 11th at 6 p.m. Central Time. So that's some good info. If you want more, that would probably be a good one to go to. Yep, you're welcome. Jetstream is another good resource. I actually used some of the images on this presentation from Jetstream. So yeah, there's more classes there, good info there. Yeah, we try to do a couple of in-person classes per year. We found that really doing things virtually, we can, a lot of times get, quite a few more attendees. But yeah, if you really want one for your local area, just work with your emergency manager and try to get that set up through us. And yeah, if we can get enough people, we will certainly come out. And we try to do it on days that there aren't March Madness games going on, or UK or U of L or whatever college team is playing locally. So try to be as accommodating as possible. It'd be great if you guys did an after action report for a significant weather event in the area. Go back through the forecast data, track the data collected during the event, basically walk through the whole thing with SPC data and local observations. So yeah, actually for almost every big event, we will do some sort of review. We'll go through the environmental data, the observational data. We'll look at individual warnings and warning decisions and see if there's anything we could have done better. If we miss an event, we definitely will review that, because we have families out there too, and nothing is more painful for us than to miss an event. So yeah, we always go back and look at those. And yeah, especially if it's a big and interesting case, we're always going to be doing after action reviews. Most of the time we kind of just keep those internal. I don't know that we release too many of those to the public, because usually they are pretty meteorologically involved, pretty in depth, even probably more advanced than what you saw here. But yeah, we certainly do that. So thank you for that feedback. Okay, Bluegrass Amateur Radio Society is on Facebook. Okay, so we will seek you guys out, and if we aren't already following you, we will do that. That way we can get access to your reports, and you guys, if you are or are not following us, you can follow us as well and get our info. Yeah, somebody asked about videos that explain radar scope. Again, can't really promote radar scope individually. Again, there's several weather apps, and it's just what you prefer. But a lot of us do like it, I can say that. But yeah, we can't necessarily promote it individually over any other one. So NWS Paducah in past years had some pretty in-depth presentations regarding advanced weather spotting. Okay, yeah, it sounds like they got, like I said, advanced and elite training. So yeah, and it sounds like that one's coming up on April 11th. So I would check that out if you want even more info. Thank you from KY4 BLY Bowling Green. Yep, you guys are welcome. Appreciate all the ham radios out there. Operators, you guys provide good info. So how much of the analysis done by human eyes versus computer? So all the examples you showed, all the subtle variations in images and fast moving, quickly changing conditions. Seems it would take an army of trained people. Yeah, so during busy weather, we've got a lot of staff in here. You need people to watch radar. You need people to do that meso analysis. Again, that changes, every 15 minutes hourly. You're getting new data, so you got to keep up with an evolving environment. We need people to monitor social media. We got the phones ringing off the hook. You still got to do the regular forecast. You got to keep that regular forecast going. You got to handle collaboration with Storm Prediction Center, with media, with partners. So yeah, during busy weather, we are busy in here. It does take an army of trained people. So that's a good point. What else did you say? You said a lot of it is human eyes versus computers. So that's a good point. Like, we still have people, and we can still do hand analysis. And the best way to still really get, I don't want to say, the best word, probably intimate with your environment, is to do a very detailed hand analysis at the surface in the, 850 millibars, which is 4,500 or 4,000 feet off the ground. The mid levels, 500 millibars, 18,000 feet off the ground. If you can quickly do those, the problem is it takes a little bit of time, and in a rapidly evolving scenario, you're usually busy with other things too. It's a lot easier to have the computer do it for you. So yeah, I'd say we do rely heavily on the computer analysis, but it does take in real observations. So it's not just like some, full-blown model data. It actually is incorporating, real observed data from, ASOSs and AWOSs and things like that, and weather balloons. The other thing I'll say is we now are kind of doing a new thing in the Weather Service where we'll actually have what we call mutual aid, where we'll have some mesoanalysts from other offices. Say there's like an office in South Dakota where the weather's perfectly quiet, then there'll be somebody that'll actually watch mesoanalysis for us while we're busy with all those other things that I talked about, helping us make warning decisions and keeping track of the environment, because the environment is really what drives storm mode, like we talked about. And if you are not up to speed on your environment, you will probably get burned on radar, whether it be false alarming by warning too much or not warning enough. And again, that comes with the knowledge of the environment. So yeah, staying on top of the environment really is the number one thing that will help you make the best decisions as you're looking at those storms evolve on radar. So, and yeah, it does take an army. So good question, good observation. Spotter numbers. I've never been given one. Given by the spotter network, just NWS issue. I know we used to issue spotter IDs. I don't really know where we stand on that anymore. That's a question probably get answered. I know some people have them, but it seems that others don't. So I feel like that's a kind of an old school thing versus a new school. I'll have to get clarification on that though, but to be honest with you, I don't know whether there are actually spotter numbers anymore, but I do know we are trying to issue those certificates, so that will be at least one way to prove that you did it. So somebody asked, is there an EF range for supercell tornadoes? So what it is, the EF scale, which is the enhanced Fujita scale, yeah, it basically, supercell tornadoes will be included in that range. So whether it be EF0 to EF5, yes, that is true. I know we talked a lot about the EF range on what you'd see from, mesovortices and squall line tornadoes. And again, those are usually on the lower end of the EF scale range, but with supercells, you can get EF0s to EF5s. You're not really going to get an EF5 tornado out of a squall line mesovortice tornado. So yeah, supercells are the most high end, and those are really where you're going to get, the potential for your highest end tornadoes. But yeah, you can also get an EF0 tornado out of a supercell as well. So good question. Especially the police officers in the patrol division. So has the NWS suggested the law enforcement, especially police officers in the patrol division, to get their storm spotter certificates? So I mean, we do encourage it, and we do go out to local communities and give spotter talks, and a lot of times the people that will be there will be your law enforcement, first responders, fire departments, emergency managers. So yeah, because they are the ones that are out and about, and they know their county locations or their city locations very well. They know all the roads, so they can very quickly relay, their location with respect to a storm or whatever they're seeing. So yeah, we absolutely do, and they are one of our most reliable sources. So yeah, good question, good observation there. Yeah, you can leave if you want. Questions have gone on for quite a while. In fact, I got to be back here at 7 a.m. in the morning, so I'm probably going to have to wrap up the questions here pretty soon too. Somebody did say MPing works great on Apple, so yeah, that's good to hear. It's not just a Droid thing. What am I seeing is mute, non-mute, full screen, minimize screen, and raising hand. Yeah, so that's kind of the outside controls. If you look in the gray boxes to the right of all those, there should be something that says handouts, if you're the one still talking about the handouts. I don't know. Like I said, I can't see what you're seeing, so I can't say either way. I'm sorry. This is from Windows, Firefox, go to webinar. Okay. It could have, yeah, I mean, maybe it has something to do with the Firefox browser. I'm not sure that maybe that's a different interface, Bailey. Yeah, I apologize. If you can't get it, the handouts, try to reach out to us via email or social media, and we'll see if we can get them to you that way. Somebody said the handouts are in a drop-down bar that shows up when you click on the slide. The handouts are under a document icon. So maybe that could be some helpful advice. All right, so cold air funnels. Somebody's asking about that. How do those form versus tornadoes and gustnadoes? Yeah, so cold air funnel is actually a cold core system type of a setup. So when we talked about that upper low, that that could develop and kind of just hang around over an area, a lot of times you'll have very cold air aloft, which gives you those steep mid-level lapse rates we talked about, and it gives you mid-level instability. But a lot of times the bases of those storms are too high, and it's generally like a 40 or 50 degree type of a day at the surface. And so you don't have the low level, basically thermal profile that would support that tornado reaching all the way to the ground. But what you get is basically like an elevated, tornado, or what we would call essentially a funnel cloud. So yeah, cold air funnels very rarely, if almost never, reach the ground, but there is a phenomenon where those do occur, and it's usually a cold core type of a system that's going to create that. And so, yeah, that's quite a bit different than a gustnado, because basically a gustnado is kind of right on the leading edge of an outflow gust front. And so, yeah, that's just kind of basically dust and debris getting swirled up at the surface as that outflow, because it is going to be gusty winds as that goes. But generally, a gustnado is not going to be connected to any sort of cloud base, and so it's not like a true tornado. So we don't consider them tornadoes. Of course, then your true tornadoes basically drop down from a cloud base and are in contact with the ground. So yeah, that's the difference between those three, but that's a really good question. So somebody gave some specific directions here. Handout links are in the control panel screen, window menu, go to webinar, control panel. Handouts listed below. So hopefully that helps you find them. Do you all do tours of the NWS offices? Just curious. Yeah, we do. It's weather dependent, so we got to have, we're not busy with weather. Generally like to get a group, together of at least, 10 to 15 people. If you're going to get 20 or more people or 30 or more people, generally we might need to do it in, multiple groups, because it's really not that big of a facility. It'd get pretty crowded in here if we had more than, say, 30 people. So, but yeah, just reach out to us and we can try to set something up on a quiet weather day. Still get to see some really cool things. So somebody said you can get Skywarn stickers on Amazon. You're probably a better source of information on that than I am, so I believe you. You can find a lot on there. So I just don't know that we really have them anymore locally here at offices. So okay, so yeah, Woodford County EMA said they have a drone if we need anything in that area. So yeah, that's great. I don't know if that's Drew Chandler. Anyway, hi Drew, if that's you, Woodford County. We like you guys over there. So thank you for everything you've done for us and any resources, much appreciated. Moving on, redcross.org will have plenty of information and trainings. Yeah, that's a good point. Red Cross, like I said, they're a great resource, not only for mitigation and planning and awareness, but in the post-event recovery as well. Okay, yep, thanks Paula. Yeah, just email is probably going to be the best way. So, and we should be able to get those to you. That's not Drew. Okay. Yeah, I just saw Woodford County EM, so I wasn't sure, but we appreciate y'all over there in Woodford County. All right, well, I think that's about it with the questions. Again, we've been going on for 4 hours now, so I guess probably a good time to wrap it up. Do appreciate you all. Again, we'll try to do this next year and change up the content a little, but thanks everybody for hanging out, and we'll hopefully look for that link to the certificates tomorrow, and we'll try to get this on YouTube as soon as we can. So take care, everyone.